dans une poche et alors ceci accroché.
Voilà.
Mettre dans une poche.
Ah. Ok.
So sorry about that. We had some trouble broadcasting the session on YouTube. It seems to work now, so we can start with some delay for which we ask you to apologize. And so we're happy to have you all around here. This is the second session of 2 workshops group where we are organizing with Nancy University, with the Archives Poincaré. This is a project which is funded by the Grande Région, which is a European regional fund, which asked us to organize things around philosophy, on the topic of philosophy of mathematics. We chose to work on intuition, but we also chose to work on that topic by combining history of mathematics, philosophy of mathematics, cognitive studies, and even education studies, because we found that this notion of intuition, had to be worked through all these aspects. So we had a very pleasant first workshop in Nancy a few months ago, and we're here for going on in this project, and we'll have 3 days with 15 speakers. As you can see, Paola Cantu was supposed to start this session, has not been able to come. She's actually sick, unfortunately, and she won't be able to be in Liège today, nor tomorrow or on Wednesday, but she could perhaps join us on Wednesday and give her talk on Wednesday. Depends on how she feels. But Gerhard Heinzmann, who is one of our partners in Nancy, has agreed to switch slots and to give the first talk. And it's on intuitive roots of mathematical understanding. So, Gerhard, you've got the floor straight away. You've got your own.
Okay. Thank you very much, Bruno. And I'm very happy to be here. And you read the title of my talk since a long time. I dedicated this to our colleague, Nancy colleague, mathematician, Jean-Pierre Ferrier, who passed over in last August. So, yes, first a surview. I show in this paper that intuition in mathematics is interpreted according to the skill model, I will explain what it is, rather than according to the common perception model, that's intuition percepts something, can contribute to a better understanding of mathematical activity as well in the context of justification as in the context of invention. Thus, intuition can be helpful for better insights into the difference between stringent and explanatory proofs. It can be used for characterizing thought experiments. It can give hints for overcoming the still discussed taxonomy of eliminatory and non-eliminatory structuralism. So my plan of my talk is first a little chapter terminological ratification, then classical difficulties of epistemic intuition, my model of intuition, then the application as intuitive aesthetic component of proof explanation, South experiments, and finally, if it's enough time, a geometrical structure in Poincaré. First, there are 4 kinds of intuition. Intuition as a mode of access to scientifically non-accessible areas, cabinet of curiosity. Intuition as an instrument in a context of discovery, similar to a flare. Intuition as an almost immediate decision-making capacity. This is Kornblit, Sosa, and so. Analytic philosophy, very discussed. Finally, intuition as a basis of epistemic concept like knowledge, rational belief, reasoning, or understanding, and I'm only interested in this fourth sense of intuition, and I will speak in a shortened way, a little bit polemically against the other specialist of intuition as epistemic intuition. Okay, with the term epistemic intuition, I mean a use of intuition in a cognitive function as a basis of understanding and justification of the meaningfulness of terms, intuition of, proposition or arguments, as intuition does, as well as on the level of justification as on the level of invention. So I'm not interested in describing the external or theory internal context where intuition is applied, but rather how intuition works. It is what kind of capacity is at work. There are three families of epistemic intuitions: sensitive intuitions of empiricists based on the phenomenon. John Locke, who opposes intuitive cognition or demonstrative cognition, is an example of such a use. Intellectual intuition of the rationalist, which concerns abstract objects, number sets, concept structures. Example of this type of intuition can be found in Descartes, who opposes intuition to deduction, in Leibniz, who opposes intuitive cognition to symbolic cognition, but also in Kurt Gödel. And finally, operative intuition in the Kantian tradition, which is associated with space and time, and where intuitive cognition is opposed to discursive cognition. Poincaré, Husserl, Brouwer, Hermann Weyl belong to this tradition, and I'm near, it's not entirely this, but I go in this direction too. Now, classical difficulties of epistemic intuition. I should mention before that it is commonly admitted that vision is a common feature of sensitive, intellectual, or operative epistemic intuition. This is why in German one speaks often of Anschauung, which is an authoritative way of seeming. Plato relates to ideas by considering visible figures, and according to Locke, in an intuitive knowledge, the mind perceives the truth as the eye doth light, only being directed toward it. So, now the most famous testimony of difficulties with intuition is Hans Hahn's talk of 1932, published in 1933, entitled Die Krise der Anschauung. As Michael Friedman Jr., he was last time here in Nancy, stresses rightly, the various crises and shifts which mathematics and this image experienced during the last decades of the 19th century and the first decades of the 20th century, the discovery and acceptance of non-Euclidean geometry, the discovery of monstrous functions, and the paradoxes of set theory all led to a radical change in the naive conception of what is mathematical intuition. On the one hand, Hilbert's anschauliche Geometrie represents a transition to view intuition in terms of Anschaulichkeit. It is in terms of making the objects visual, which is only one aspect of what the term Anschauung meant naturally in Kant. This transition was already present at the end of the 19th century, which developed modern logic accompanied by deductive rigor, so that intuition is eliminated from proofs. On the other hand, Hahn presents another view which considers mathematical intuition as dependent on the community, even as adaptable, which may be even thought at school. First, instead of relying on Kant's conception concerning intuition, one should turn to a complete logical formalization of mathematics. And second, concerning multidimensional and non-Euclidean geometry, Hahn notes that if one will suck them, the multidimensional and non-Euclidean geometry, in with a mother's milk, then nobody will think of saying that these geometries are contrary to intuition. They will be considered as deserving of intuitive status as three-dimensional Euclidean geometries today. For this is not true, as Kant urged, that intuition is a pure a priori means of knowledge, but rather that it is a force of habit rooted in psychological inertia. Now, in fact, Poincaré is teaching since 1887 that at least a Kantian pure intuition is not acceptable in geometry. The doubt that since the earliest times accompanies the intuitive obviousness of the parallel postulate is confirmed by the existence of several possible geometries. Even if one disregards the necessity of the Kantian pure intuition, this latter seems not to be able to give us an unequivocal and infallible understanding of the new geometries. Also, Bergson argues that there are things of which a philosopher feels unshakably certain. By the impetus of intuition, it is falling into disuse, not only as a criterion of rigor for inference, but also as a cognitive means in general. Intuitive description of natural phenomena are replaced in favor of quantitative laws of an idealist nature. This tendency manifests itself most clearly by Moritz Schlick, who excludes intuition from knowledge in the strict sense, because it only contributes to the acquisition of an experience whose subjective character is distinguished from the objective character of knowledge. Like Peirce, he asks whether intuition fulfills the necessary condition that is traditionally required of knowledge, and gives, like Peirce, a negative answer. His argumentation is based on three premises. Intuition is an immediate, non-conceptual belief. Second, intuition is expressed by a vague binary relation of the type a person P intuitively recognizes an object X. The knowledge relationships is at least tertiary. It has in the simplest case the form P recognizes X as Y, reducing the unknown element X to the known element Y. So, his conclusion, intuition does not take the form of knowledge. The term intuitive knowledge is a contradiction. Naturally, this conclusion does not mean, according to Schlick, that the phenomenon of intuition is non-existent, but only that it should not be confused with philosophically scientific knowledge. Intuition only expresses an erkenntnis, I don't know how to translate it in English, un vécu en français, perhaps an experience. And indeed, the assertion that any continuous function is exactly reproducible in a drawing, or that the extension of any property forms a whole, the axiom of comprehension, seems to be prima facie intuitive, though one has no belief in their truth, and though one is most attentive in Descartes' sense. Thus, the assumption that epistemic intuition is not knowledge in the sense of a true and justified belief, or even not a belief at all, traditionally allows three conclusions to be drawn. First, formal conventionalism, so without intuition, the naturalist account of intuition and the anti-naturalist account of intuition. Because I speak of intuition, I do not speak about Carnap. So, although naturalists and anti-naturalists have in common to abandon the infallibility of intuition, each side blames the other for categorical confusion. Sosa against conflict. The anti-naturalist says, If the naturalist uses intuition, he must defend himself from using a philosophical tool, prima facie evidence. Or he must be able to explain how one can account for the evidence from our empirical beliefs. You know, perhaps also this argument, famous argument of Indica, he says, oh, analytical philosophy always is based on intuition of sort of South experiments of on this, but this is only opinion in Aristotle's sense and not intuition in the sense naturally as a basis of understanding. If he does not use intuition, the naturalist, how can the reliability of scientific theories be guaranteed? And the naturalist says, if the undernaturalist uses intuition, either relying on externalism or on the authority of the first person, he does not realize that he is thus relying on a psychological common sense, which is a priori only in appearance. So this is the situation of the argumentation and the modern discussion about intuition in analytic philosophy. Now my conjecture is the following. Is it not imaginable that intuition is a simple seeming, that is vision which presents itself as necessary, is neither based on pure data of experiments nor on a pure data of reason? This is the common argumentation. Perhaps it is possible to conceive the identification contained in Schlick's ternary relation P a knowledge X as Y as governed by a semiotic process leading to a simple but nevertheless cognitively penetrable identification, such that an intuition is more than merely bound reasonable doubt, and yet that it need not be certain. It is certainly not a priori. Now in the next paragraph I will briefly give an account of my semiotic analysis, how we can perhaps find a way out to the dispute waiving anti-naturalists and naturalists, and give to the question the respectable theoretical foundation they search for giving by their search for by giving the skill model of interaction. That's what I'm doing. This identification. Schlick identifies X as Y. And I say this identification should be given in a semiotic way as seeing, X seeing as Y. So I come to my theological skill model. Instead of opposing realism and anti-realism, empiricism and rationalism, naturalism and anti-naturalism, I oppose, I think, more deeply two models of knowledge, perceptual model and the skill model. The skill in the sense of an aptitude of the mind. In the perceptual model of epistemic intuition, the adequacy provided by the intuition is judged to be between the thing, a token or type, and a representation, or if one supports a phenomenological approach, between the thing and the degrees or types of feelings. In the skill model, the adequacy provided by the intuition is situated between the actor and the represented. Either the epistemic approach is substituted for an ontological intuition of an object, or semantic intuition that a proposition is reliable approach of intuition. Now, the most known perceptual model of intuition in mathematics is that of Parsons, Charles Parsons. And one assumes an analogy with perception. Okay, and more precisely, one says that intuition finds its source in perception. Parsons starts its explanation of intuition arithmetic with a concatenation of strings of strokes. Intuition is the capacity to recognize. Now, this is the most important thing, that you understand exactly what this means in my critique of Parsons. The perception of a token as type. Think about this. Parsons said, I can percept something as token of a type. This is not true. You cannot percept something a token of a type. If you have a token, you can percept something execution of a token. But you cannot percept a token of a type. This is already, presupposes already intuition. You think about it. You can see that this is a singular, but you cannot see it as a particular. Or you can see it not as it a token of a type, you can see it as is something, but not as a token of a type. So this is a methodological mistake of Parsons. And even now, if you say, okay, I should have intuitions on I cannot percept, I can percept something singular, and then I have to do it to token, and then to token of a type. That's just a stage more. Parsons' solution is not very satisfying, because he cannot not even explain that the complete induction is intuitive. So there is very limited use of mathematics, and in fact, if now we are in the turn of applied, from the turn of particle turn, if you look what the mathematician is doing, naturally he uses intuition on a high level in mathematics. How to explain this? What sort of activity is necessary to explain this? Okay, now I propose for this the skill model. I argue for the thesis that epistemic intuition does not depend nor on the nature of objects, nor on the type of cognitive faculty used, perception or intellectual intuition, nor on the level of the semiotic system used, preconceptual first order or the higher order, but stems from a difference between the semiotic functioning of the action systems imply. So the question, what is intuition, morphs to the question, typically Goodmanian, when is there intuitive use? Now, the central idea of the construction is the following. Is it possible, on the hand, to relax the closing relationships that Schlick emergence for the intuitive act between subject and object, and, on the other hand, to weaken the identification contained in the ternary relation as governed by a semiotic process? I say P sees X under condition Y, and not P is Y, but P sees X under the condition Y. If this were the case, one could see an internal structure of intuition and to show that this is not cognitively impenetrable by distinguishing between what one intuits and how one intuits it. The mode of justification would then depend on the mode of action. If one sees X only under the sign of Y, then one intuits X. Thus, the cognitive force of the intuition would be behind a reasonable doubt and below an a priori certainty. Symptom of epistemic intuition. Let us assume that elements of a semiotic systems are used from the perspective of a dialogical learning of a sign, the later being interpreted as a language game of actions. Now, there are a lot of theory now, I presuppose. Naturally, this is, should be embedded in a dialogical approach of philosophy of language. And I cannot, perhaps in the discussion I can discuss this. So this use is a symptom of epistemic intuition if the singular and the general aspects of the action pattern are interdependent, so that the sign is not used as a representation that is independent of the situation of use, and so that the demand of legitimization of the sign's representation does not arise at the same level of reflection. It's a little bit complicated. Take an example, a Jastrow, duck, rabbit. You see it the first time. And then I see, oh, I see, you say I see a duck, I see a rabbit. Then you remark, what you see first, it was in a situation, in the contextual situation, dependent on context, and you presented it, but you have not a representation. It is not the you closed not, Peirce would say, the icon as a showing of possibilities to close it. You see it, you cannot, it is a seeming, it is necessary for itself, but if you reflect on it, if you represent it, then it is, you see that you can have a duck and a rabbit. So, a presentation is only, depending, and it is the general presentation is always a singular present as general. And this general is not, and is in the interdependence of the individual. So paraphrasing Goodman, we can say that immediacy becomes a question of interdependence rather than a question of intimacy. Now, naturally, this concept of intuition helped to understand Aristotle's big problem of distinction between nous and epagoge in the Analytica Posteriora. He helps to understand that Descartes can say that the cogito gives a intersubjective first person and not only a first person in the moment I see it, I think. It can help to distinguish in Kant, to understand this 100 years old question, what is exactly the difference between the form of intuition and formal intuition? It makes it possible to understand Locke's difficulty to distinguish the white as a concept from the white as this instance and this problem of ideas, and it can be useful, I think, for certain cases in mathematics too. And this I will show you in the next chapter. First, an intuitive aesthetic component of proof explanation. Poincaré says in Science and Method, when the logician has resolved each demonstration into a host of elementary operation, all of them correct, he will not yet be in possession of the whole reality. That indefinable something that constitutes the unity of the demonstration will still escape him completely. Wittgenstein remarks in the foundation of mathematics. Everything that I say really amounts to this, that one can know a proof truly and follow it step by step, and yet at the same time not understand what it has that was proved. Now, to clarify, it might be helpful to distinguish several types of understanding. I discussed this in the last month with Janet Folina. That of understanding the meaning of a theorem apart from any proof, such as of a theorem sentence. If you can understand the meaning of a theorem sentence, a Goldbach conjecture, you can understand the meaning of the sentence. You can understand each individual inference of a proof, one at a time. You can understand the unity of the proof. This is the synthesis of the inferences. This is Poincaré's problem. How to understand the unity of the proof. You can understand why the proof justifies the result, why it is a truth ground. This is Wittgenstein's problem, and naturally very famous Cantor, I see but I don't believe it. He wrote to Dedekind in 1877 to express his dismay at his proof that there are on a segment of length 1 as many points as in the square of length 1. So, now according to my operative approach, knowledge of a theorem requires all four types naturally of understanding. But it's a complicated thing to know what it means to prove a theorem. But in the following, I will myself limit to the proof understanding as problematized by Poincaré. What is the indefinable something that constitutes the unity of the demonstration? Note that classical mathematician says, oh, what? This is not interesting because there are Bolzanian evidence. Naturally. Classically, a stringent proof is obtained by the Bolzanian reduction of the validity of an inference between judgment to a logical consequence among propositions. But if you make this, the question is solved, naturally. There's no problem. But the proof is judgment. You cannot, what happens? This reduction eliminates naturally Poincaré's indefinable something and at the same time our proof understanding. You cannot understand the synthesis of the proof. You postulate it. It is so. To go from proposition to sentences. Okay. Now, two possibilities. One can argue that one has to use a new logic which formalizes synthesis of proof steps for rendering mathematical reasoning more understandable. This is naturally Hannes Leitgeb solutions. I propose another one. As Poincaré, I should propose another one. Mathematical reasoning includes necessarily categories of specific mathematical representation and links the content of the premises to the content of the conclusion by using not only conceptual beliefs. And this is what makes some mathematical ideas better than others. According to Poincaré's account, understanding of mathematical reasoning exceeds reasoning conceived as a sequence of propositions whose premises and conclusions are identified by means of models of a certain type. On the contrary, understanding links the content of the premises to the content of the conclusion by using intuitive seemings. Now, a symptom of intuitive explanation. A mathematical proof gives an intuitive insight in the relationships between premises and the conclusion if it contains intuitive language use. That is, if parts of it can be interpreted as exemplifications of general idea. When parts of the proof can can interpret it as exemplifications in a good modern sense, as semiotic exemplifications of a general idea. The insight increases in proportion to the intuitive proof stage and in proportion to the involved semantic density. And this replaces the strong purity criterion. Now, an example is the proofs of irrationality of the square root of 2. You know the indirect proof. You have nothing to understand. You suppose that the square root of 2 is rational, and then you have a contradiction. Now, a short proof of the irrationality of square root of 2 can be obtained from the rational root theorem, that it is Px is a monic polynomial with integer coefficients, then any rational root of Px is necessarily an integer. You begin completely different to prove. You say not that square root of 2 is rational. You say the square root of 2 is x. And then you have a polynomial 2 equal x2. And naturally, we have the polynomial px equal x2 minus 2. It follows from the root theorem that the square root of 2 is either an integer or irrational. Because square root of 2 is not an integer, it must be irrational. Okay, now the polynomial x2 minus 2 exemplifies the unit general polynomial with integer coefficient. You can see this, but it is not logic. It is not a. You can see it now that this is a polynomial. Now you can say this proof seems to give a better intuitive view than the first proof. It proceeds by interdependence of global y question with a local y question. A polynomial equation is instantiated by a monic polynomial equation that exemplifies this and that is finally submitted to special valuation. The integer 2 is not found under the strong intuitive representations of x2 for integers x. The fact that the singular seems in this case 2 singular with respect to the general could be overpassed by a series of further exemplifications. So now this is very mathematical, and this was done by Jean-Pierre Ferrier to show that the root theorem can be proved by all steps of so intuitive exemplifications. Because normally you say, so you presuppose a theorem which is much more naturally abstract, but you can do it. So it seems likely to explain that square root of 2 is not rational by the fact that x2 minus 2 is a monic polynomial with integer coefficients. Now, next, how many time? I see 25. Epistemic intuition as a frame for mathematical South experiment. This is naturally now an example in the context of mathematical heuristic or of conjectures of the context of invention. But I give not the condition under which this conjecture are possible, but I look what happens, what sort of intuition is in play, and I suppose it is this my skill model of intuition. Let's look at it. First, I should explain what I mean by a mathematical formalism. To use a mathematical formalism means two things. The proofs are unshored in the grammar and standard of logical and semantical norms of the time, which makes them rigorous, and they are based on mathematical results found in the existing network. So we have something and you use it. And these results constitute the experimental domain with respect to proof and construction of the formalism, and they are used in a functionally analogous way in which physical data can be viewed as a realization of a theory in the natural science. But naturally, if I will explain something, that something is a mathematical South experiment, I should first explain what is a mathematical experiment. So, experiment is if you use a formalism with respect to the given network of mathematical existing sciences. This is our domain in mathematics, our experimental domain. Now, definition, mathematical experimentation. The pivotal element of mathematical experimentation is the attempt to confirm a theoretical language use by an observational language use. Here, naturally, I presuppose Sellers' insights of the myth of the data. You cannot, you can say, oh, I cannot agree. Okay, we should just discuss now about Seller if there are given theory independent data. I think Seller is right, don't exist. And if Sellers is right, then the question is between, for experience, is between theoretical use and experimental use of language. And to ensure the validity of a level n by an evidence-based inference from both the construction objects and construction as objects of level n minus 1 or more. This means, not here completely formal, the existent domain. If you refer mathematical experimentation is to refer to something what this is. As you always read in mathematical text, as we know this I mean this referring to what exists, to an experimental language, in an analytical way to speak, a philosophical. Now, mathematical thought experiments. In mathematical thought experiments, we take recourse, based on mathematical experiments, to a modal deviation using further semiotic means. Epistemic intuition provides us with access to these deviations as genuine possibilities of mathematical inferences as opposed to pure fictions. The South experiments should be opposed naturally to pure fictions. How to manage it? That is not fiction, but it is just a modal deviation. This accessibility is the justification for the validity claim concerning mathematical South experiments. I take the Basel problem. It was presented by our colleague Philippe Lombard in Nancy. One is interested in the limits of the series of the 1 over n2. So this is converging very, very slowly. Now in the 70s, Leonhard Euler published, Basel naturally, published different papers in which he calculated an approximation of the sum with 6 decimals. So the 7031. And in 7034, he recognized in this result the approximate value of P2 over 6. Now, how it managed this? What was this idea? And this was a typical South experiment. The Taylor development of a function in the form of a series is known since 1715. In particular, the function sinus x is written as an infinite polynomial. And you can transform it to have a 1. But we know the roots of this function, naturally. They are the non-zero value of x that cancels sinus x. So these are the p, 2p, 3p, and so on. So now let us boldly assume that we can express this infinite series as a product of linear factors. But naturally, if you have a polynomial, you can develop it by a product of factors of these solutions. But you cannot do it here. We'll try it. We do it. Then the term x, x2, is precisely this one I wrote down. You see already, we are very near the formula of our what we are searching for. And from the original infinite series development of sinus x over x, the coefficient of x2 is, you can do it, is minus 1 3 factorial. So, and now that this is minus 1, so 6, and the two coefficients naturally should be equal. Therefore, this should be equal. This one should be equal to this. And now you see P2 over 6 is exactly this sum. Okay. Now, here's the analysis of this example. First, the preliminary calculations constitute the first level of mathematical experience. First, Euler calculated it, and then he says, oh, it's very, very slow. This helps Euler's guess within the approximative values obtained, the approximation of the exact value that he advanced. The general theory involved includes the definition of a polynomial and decomposition into factors involving the zeros. We must know this. Its field of application includes all polynomials. Now the overshoot by transfer in Euler's proof is the following. It's the following. I should. Okay. One sees that the function sinus x and the indefinite product have exactly the same roots and have the same value as x. And so Euler asserts that they describe the same function. Euler is correct that they describe the same function, but these reasons are insufficient to guarantee it. For example, the Euler, the function x, sinus x over x, also has the same roots and the same value at x, but it's a different function. So it was not correct. What is done is the following. Now I have no. You have polynomial s of level n minus 1. So what is given? And this is a singular element of the general idea, the combinations of power. You have a polynomial and you have the idea. I think it is can be written as a combinations of powers. This is naturally is an interdependent, intuitively linked. So you see this intuitively. Now there is a theory T. Naturally, you can prove it does. if it is a polynomial, you can decompose it as factor of the power, a theory T. And now the theory T, the S is an instance of T. S and different S are instance of T. Now S prime looks like a combinations of power, but it is not exactly, it passes not by the theory. It is not, you cannot say that an infinite series can be is a polynomial which can be combinations of powers. But naturally, you can write it as a combinations of powers. So here you have to the idea, it is the same. And this idea is symbolically executed by a theory T. And so you see this is a deviation who transfers in fact this R, this is an instantiation in a I. The method used by Eulers sees in an apocryphal Y the relevance of a result without being able to prove it by logical means. It is a thought experiment. A modern mathematician will be able to draw a rigorous proof of the higher level of analysis of what Euler did with the framework of within the framework of the Eulerian products. So later, this false, a little bit deviation proof, you can reformulate it in a correct, in a today accepted proof. Okay, here already, now, I don't know, I speak already 49 minutes. The last, I think I will not, it's a little bit complicated, the last chapter, it means that, just I recall what is the result. You should know how Poincaré constructed geometry. It is by sensations, and sensations represent intuitively a group, a theoretical group, and you have extensions of the group, the models, and this intuition is as a deviation as it was in the South experiment. Finally, you can express it in this way. So, to summarize, at least since the practical turn in philosophy of mathematics and logic, efforts have been made to better understand the informal reasoning of the active mathematician, and thus come back to Poincaré and Peirce's pragmatic critique of the formalists and logicians. One of the main challenges for the connection between pragmatics and mathematical praxis is to explain the dynamics of mathematical thinking. Now in this chapter, the application chapter, chapter 2 of this lecture, I set out to show that epistemic intuition viewed from a pragmatic perspective can indeed help to shed light on some classical problems, not only of philosophy, but even of interpretation in mathematics. The choice of problems discussed might seem arbitrary, and to some extent it is. I hope, nevertheless, that they have a paradigmatic character, but so I'm not sure how many of mathematics can be explained in this way, but it's a tentative work in progress. Thank you.
sorry, just wait for a minute. Could you just tell your name, and then so people online will hear who is asking the question.
Okay. Yeah, my name is Jaroslav Lajos, and I'm from University of Oklahoma in the United States. Well, yeah, I think one of the statements that you highlighted is that recognizing token as a type, which
Yes.
I mean, it resonates with me, but there's a lot of complexity in that. What is a token? What does it mean to recognize something? What is a type?
Yes.
And
Yes, you.
can I think of it in terms of trying to explain token is something that doesn't have meaning yet. It's a new thing. Recognizing is a mathematical technique of associating something, and the type is something that we already understand. So would you say that this whole thing is a way of mapping new into something that we already understand? Or and it's not going to be one-to-one mapping. It's going to be some kind of a partial relationship association. Would that be a correct way to think about it?
Yes, I have to explain how I consider this token of type relation. In fact, it is the basic relation for understanding a singular atomic sentence. If I say this is a chair, how do you understand? How can I justify it? I have to first. We have to learn what means chair. I say this chair in a dialogical situation. Chair, no chair. Chair, no chair. Chair, yes. Oh. And then so we by instances, different instances, reconstruct the concept chair. But then it is not sufficient, because we have only this is a chair, this is a chair, this is a chair, this one. But to say now in a predicative way, all chairs this is a chair. This is different. Now you use the concept chair who had learned to instantiate other things. You use it predicatively. So, and this dialogue presupposes that you understand execution. This is a chair as a representation. You, what is say, this is a chair I present for you, and you should interpret it as what I say, as you should, this is the execution and you see it. So this is the passive part, and for this understanding is necessary to have intuition. And this is the foundation of epistemic intuition. This I have a model for understanding things. So you see that the type and token difference are at different levels. So in a predicative sentence, the subject is not an instance of the predicate. This is more than an instance. On the appredicative level, there are instances. You have to know different instances to know one concept. And if you have a concept, you can have propositions. So, but naturally the type and token are both already on a theoretical level, because the construction of tokens is only in relation to types. You cannot say, I see a token, I see an execution, and only if you see this execution as execution, I can say it is a token. This is a little bit complicated.
The thing that I find puzzling is in this process we have these types. It's something we already understand, we feel familiar with. We recognize the token and explain it in terms of something we already know. So where is the new knowledge coming from? Okay, we have...
In the dialogue.
So that process introduces something new, some new knowledge. Yeah, that's kind of the puzzling thing. How does that happen? That all this kind of fascinates me.
Yes,
But,
this is in the underground of what I am saying.
Yeah, I really love the
Okay.
Thank you.
Any other questions? I've got one, but may I ask it? Because I will have to leave in a few minutes. I was wondering, when you introduced this Euler's discovery, you almost claimed that it was some kind of trial and errors experiment. So he found out. I mean, he found out that it was close to the
first situation
pi over 6, and then, but because he made some tries, and
but the trials are based on intuition. This is my my argumentation. It is not fictional. It is because I mean infinite series. It seems to be a polynomial with the decomposition theorem applies, but it does not apply correctly. It applies in a deviant way.
Okay. So, but you suggest that he probably made other tries also, or
no?
He went for this try.
Necessary.
Okay, straight away. Okay, because of the intuition.
It's not necessary to do other. It's not a trial, so I think
okay.
No. He has a deviate resemblance, a resemblance with resemblance. That is not the same. It is always the same point. I will transform the equation, identity, in C as.
Okay.
C X C as Y, and not X is Y.
Okay. Thank you. So, Romain Buchy.
Yes, Romain Buchy from University of Zurich. My question concerns the relation between what would be intuition in the more Kantian sense and what you call epistemic intuition. And with respect to counterintuitive results in mathematics, and counterintuitive in the sense that goes against spatial Kantian intuition. Take, for example, Banach-Tarski theorem or paradox. Yeah. You can decompose a sphere into finitely many pieces and recompose it in or reassemble it to two spheres that are equal to the first. So you have here something counterintuitive to our spatial intuitions. Is it possible, and that's my question, is it possible with your notion of intuition to arrive at this kind of intuitive understanding that goes beyond just accepting the theorem as right because you have a demonstration that is logically? Is it, and how would it work in such an example, or maybe another example?
I cannot answer exactly because I should study the example. But naturally, if you say it is counterintuitive, it is counterintuitive for the perceptual model. Perceptual, naturally, the comprehension axiom is very intuitive, and it is false, and there are contour This is naturally the length of one and real numbers and is counterintuitive, but it's right. I'm not in the, if I say intuitive, it's not in the perceptual model, but in the skill model. Now I cannot answer your question without, this is the problem I discuss. I cannot say that it works on all for all cases. I don't know.
But you would be ready to say that it's possible to have epistemic intuition that somehow trumps like the spatial intuition, that it's possible to have intuition in cases where it's counterintuitive in a spatial sense.
I think so. I think so. Because I can solve all the so many problems in the history of philosophy, and then it was nobody explained correctly what is the difference of mathematical experience and mathematical thought experience. There was, they never defined it very well, and I can naturally, my definition can be contested. If you are not, have you not a seller conceptions of the relations, that there are no theory-free data, all my conceptions fall down. So this is in philosophy, is always what are your philosophical presuppositions? So but I said, my philosophical presuppositions are a dialogical model which is in the cellars. So for this, there are no pure data. And then the difference between experiments and is the experience can be explained as the difference between theoretical language and observational language. How there are the relationships between the two languages. This okay.
Thank you. There any other question? Yeah.
I have a very small clarifying question. When you spoke of Schlick's text, you were talking about Peirce, and I wondered, is that an explicit reference that he makes? Because it also reminded me of some of William James' writing on intuition and reasoning, and so I wondered the strength of that connection between Schlick and Peirce.
Between Schlick and Peirce, I just was saying that Peirce also refused as Schlick intuition as knowledge.
Mm-hmm.
But both say naturally there are a phenomenon of intuition, but it should be outside science. And I naturally introduce it in science by Poincaré, by saying you should interpret semiotically the relation of identity.
And is Schlick citing Peirce in this work, or are they arriving at that conclusion?
Yes.
Okay.
I can.
Yeah.
I have not yet here, but in my book it is quoted.
Because I've also seen in William James's text on psychology, he has a similar viewpoint to Peirce, which
Okay.
makes sense. Thank you.
Okay.
Thank you. Any other question for this first talk? Yeah,
Yeah, maybe just a quick question about what you wanted to say at the end. So, can you say something about like your conception of epistemic intuition and structure? Was there something you wanted to add? Not.
Okay.
Or quickly, if it's possible.
Yes,
if not.
This reflection is based on very, I find it a very detailed critique of my friend von Bülow of the dispute between the name who is the name of Quinon's master supervisor who is writing about structures in the United States. Shapiro, yes, thank you very much. So about Shapiro and Heinzmann and all this who interpret structures as ontologically important, and the problem is how can places defined in structures is a structure as an object, or should be a structure not be object is one. And so von Bülow argues to conceive structures as universals which are just given by instances and general. And naturally, this is Poincaré's concept of a group, because a group concept is pre-existing in the mind, and his theory of sensations exemplifies the group structure, but not directly. It exemplifies just, and so if naturally here in this sense you have not a structure as a model. It's a structure. It's just an idea, a general idea, and this resolves naturally the problem of places in the structure, but it is coming from my work with Petitot to interpret structures not ontologically but in functional. Structure has a function, and the group has a function, and it's not ontologically interesting, but functional interesting. So to switch this discussion in the United States, where structures are always conceived under the isomorphical point of view, and mean this is completely absurd in mathematics, that structure should be, they're not interesting isomorphic structures. Groups are not isomorphic. There are a lot of different, not categorical, and this is the way in practical mathematics to conceive structures not in a purely philosophical way, in an ontological interested point of view, but in a functional point of view. So this is.
I see. Thank you. I think maybe it's time to wrap up for today. So let's thank Gerhard again. So we are 15 minutes late, so we go for a 10 minutes break and reconvene, and we just move the lunch 15 minutes. Okay, there should be coffee somewhere, and okay, so you can go on the back and. Ça va?
1h10 exactement.
Voilà, c'est ça. On est en retard, mais ponctuel.
Voilà, ponctuel, voilà.
Très bien, c'était une bonne conférence d'ouverture. Vous êtes Nicolas, Michel, c'est ça? Alors, il faut une minute, ça marche. Attends, on va juste deux trucs. Tu m'envoies le numéro de Emmanuel? Oui. Ok, super. Et les sandwichs, t'as pris des.
I should give this one.
J'ai deux petites contraintes cette semaine-ci. Mais vous irez vous regarder ce soir sur YouTube.
Ah bon, parfait. What alors? Attends, ouais, on va regarder. Je crois que j'ai le Recherche à Londres alors. I may reconsider at some point. Because the problem is that like, you have too many intermediaries.
There's 64 kilobytes left on your disk.
I have to suppress things. Can you eject it? I will try to. Or you can go to your mail there if you don't mind. Do you mind going to your mail on your office computer or are you? Ça te vient d'aller sur tes mails dans ton.
Non,
Ouais, t'inquiète pas. Je dirais pas parce que c'est peut-être.
ouais.
Si tu veux, tu peux te l'envoyer. Ah, mais en fait, mais non, maintenant t'as un.
Ouais, mais
T'as un
bon,
Google. Ah, bah c'est super. Ah,
mais je trouve, moi, sinon je l'envoie. Ouais, c'est un Google.
Ah, mais attends voir parce que. Ouais.
C'est juste que là, ça stream ou pas?
Ah, oui, d'accord.
Ah, je sais pas, juste. C'est bon, ouais. Tu vois, j'arrive pas à l'éjecter à chaque fois, je sais pas pourquoi.
Ouais, non, mais.
Fermer.
Il y a 50 000 trucs là.
Tac, tout fermer. Mais moi je fais juste comme ça. Bon, je l'enlève comme ça.
J'essaie d'en trouver une un peu.
Donc ça s'appelle Liège Intuition.
Mm.
On a un travail là-dessus.
Si tu fais ça, je sais pas, ça marche ou quoi?
Ah, ok, super.
Ouais, parfait.
Ça va, c'est bon.
Ouais, c'est bon, c'est bon.
Enfin, moi,
Vas-y.
je reviens.
Ouais, pas de problème. Ça marche. Tout est bon. Tu veux vérifier quelque chose sur le stream ou c'est bon?
Non,
Ok. Parfait.
Okay, so we're going to resume again the second talk of this morning. And so we have Nicolas and Michel from Wuppertal who's going to talk about the Zeitler and holistic nutrition. Thank you. The floor is yours.
Thank you very much. And so thanks to the organizers for having me here. I think looking at the program, there'll be lots of intersections between what I'm going to speak today and many philosophical and historical themes. So looking forward to the conversation. Okay, so I'll mostly be discussing today the views of Hieronymus Zeuthen, a Danish mathematician, alive for mostly the second half of the 19th century, whose career was pretty much entirely devoted to geometry, from his 1865 doctoral dissertation in Copenhagen, which followed a brief stay in Paris, where he studied under Michel, up to his 1914 definitive treatise on the enumerative methods of geometry, a treatise that I will be focusing on early on. Over the course of this whole period, he also wrote several texts in the history of mathematics, which some of you may know better, including his defense of the now infamous geometrical algebra thesis, And so he was a contributor to both mathematics and history of mathematics in correspondence with many European mathematicians like Félix Klein and French mathematicians and so on. So really a figure that is now forgotten perhaps in the history of mathematics to an extent, and who suffers from his being in Denmark, so in circles that haven't been the subject of much attention, but someone who was really very much at the heart of lively fields of research like algebraic geometry, and in connection with many of the big names of the history of mathematics at that time. And so what I will start with is his 1914 address he gave at the Copenhagen Royal Academy of Sciences, in which he was to present so the aforementioned textbook, which he had finally put the last word to, a book which had taken him over a decade of writing, and which was in a way the crowning achievement of this decade-long engagement with geometry, his final piece of the geometrical wisdom, which he was then to present proudly to the Academy in front of a very, very diverse crowd. So this is a commemorative painting of the Royal Academy of Copenhagen, roughly from the same period of this address. So to the right you have Zeuthen, and circled in red on the left some names that you might know. So to the very left is Heidelberg, the philologist who edited Archimedes' palimpsest. The third from the left is Christian Bohr, the father of Niels and Harald Bohr. And the last figure that I circled is Harald Høvding, a philosopher that you perhaps do not know much about, but who will play a key role in this story. And many other scientists from pretty much all possible fields. So really not an assembly of mathematicians, but of scientists from all fields. And so in order to, it's too early. In order to present his book to this diverse crowd, Zeuthen could not really rely on mathematical technique and present the content of his method, but rather had focused on a more general description of his work and tried to summarize the general direction of his approach to mathematics in a way that his contemporaries would understand. And so he set out to talk about the relation between computations and reasoning in mathematics, but also in science in general. And I will read this quote. I wish to explain to you, who are not mathematicians, the relation in which my endeavors stand with regard to those which are more embedded in the widespread trend of the scientific world of our time. The question of the relation between the use of computations and reasoning in mathematics is but one aspect of the general question of the scientific use of symbols in the extended sense in which Bergson takes this word, and intuition. So here, symbols in this Bergsonian framework refers to any word, symbol, what we call symbols, diagram, any form of any means of representation that we use in a law-bound fashion. And so, for instance, Zeuthen refers to the code of law, a set of laws, and for instance, of punishments, which are to be read in a very law-bound, in a very mechanical fashion, and the way in which we actually carry out judgments in a court, which is more fluid, which takes into account more nuances and particularities, which would be then on the side of intuition. And so Zeuthen's idea was to say that mathematics, this divide between intuition and symbols in these very general senses was fundamental, and that his own work was firmly on the side of intuition or reasoning, these two words being quite strongly associated. And so he wanted to argue that in mathematics, intuition plays a key role that symbols cannot pretend to achieve as well. And in order to explain that, he referred back to his own mathematical education in Denmark and talks about this professor, Steen, who said something like this: I do not find a mathematical result well-founded until it appears to be fully secured by computations. But Zeuthen continues, I could not nor wanted to forego what I call reasoning or intuition. As I strove to satisfy in my own way the demands for formal clarity of my able teacher, this came to be even more to my advantage than I had sought to fulfill it in the way that he most narrowly prescribed. Moreover, both then and later, as a historian too, I could on the contrary see the danger to which the computer, so the person who computes literally, is exposed. He may in the first place compute incorrectly, use the prescribed methods incorrectly. And it may happen that precisely in this comforting confidence, sorry, this is my rough translation from the Danish, precisely in the comforting confidence in the certainty which computations provide, he goes beyond the boundaries within which they are valid. The danger arises as the computer, busy with his operation with computing symbols, forgets to reason about their proper use. in a nutshell, the idea being that computations, because we associate with them the values of rigor, of certainty, of being error-proof, tend to be dangerous in that way, that we forget that we must control when we can use them, the boundaries within which they are valid, that we may let the symbols carry us forward and further than we should really go, whereas a critical use of intuition supposedly will prevent such errors summarizing. So those are very general and perhaps hard to understand statements at this stage. But what I will try to do today is, first of all, explain why and how Zeuthen mobilized this Bergsonian theory of intuition to account for what he had learned from these decades of engagement with algebraic geometry. So to connect these decades of practice in cutting-edge geometry with these more general pronouncements, and also to flesh out why the reference to Bergson became meaningful in 1914. Oh, sorry, this has gone weird. I will also try to reconstruct in Zeuthen a sort of a philosophical position, but also a mathematical practice that, in a way, cuts across usual descriptions of early 20th century views of symbols, intuition, geometrical truth, rigor. We will see that in his critique of, for instance, axiomatics, he nonetheless takes a position that is quite unusual and doesn't really sit well with how we usually think of that period. And lastly, I will use this case study to argue that the history of mathematical intuition must be viewed against the backdrop of other histories, mostly here theories of in history of psychology, philosophy, but even ethnography. So as a way to call for an opening of the history of mathematics to the history of other forms of knowledge, which I think is necessary if you want to understand what Zeuthen was doing here. Okay. First section. I'll check on for time. First section is what Zeuthen calls the relative generality. He doesn't call it the theory, but it looks better this way. Okay. So here's the part of the table of content of this 1914 textbook, which he had presented at the Royal Academy in Copenhagen. And looking at the table of content for the first chapter, we see some surprising entries. For instance, the meaning of numbers, but also a bit later, the relativity of the concepts general and special or particular. And so the idea that in geometry, the first thing that you must learn is what do numbers really mean, the numbers that we whereas like the degree of a curve, for instance, what do these numbers really mean, which might seem to be something not in need of a definition, other than technical definition, but yet something that Zeuthen devotes the first pages of his textbook to. And more strikingly, the idea that any statement that we will find in this textbook has to be taken as relative, or at least the generality of any statement, of any theorem to be found in this textbook is to be read as relative to a certain conception of generality. So what does this mean? Well, a way to understand that is through Zeuthen's recollection of the so-called duality dispute, which Jemma knows much more about than me, but which I will briefly recollect. So some of you might know that Gerhard, who was the editor of the Annales de Mathématiques in the 1820s, developed this way of presenting geometrical results in parallel columns so as to highlight the duality between certain statements. So the idea being that in many geometrical configurations, for instance in the plane, you may switch the words like points and lines, coinciding and intersecting and so on, so as to obtain for free a second theorem. For any geometrical theorem, any projective geometrical theorem in the plane, you would gain a second one for free just by switching words around in a certain fashion, in a certain manner. But this had led him astray because in a paper in 1827 he thought that we could do that, for instance, for the definition of the order of a curve. So the order of a curve is essentially, given a plane curve, at how many points it intersects a given straight line. And so this is what we consider to be the degree of the polynomial. And he thought that we could say that from so replacing the given straight line by a given point, and replacing the intersection by tangencies, which is the usual procedure, we would find that there are as many such intersections as there are tangents that we can draw from a given point. And this turned out to be false. So you have those transformations that relate lines and points. I won't get into the details, although we can discuss them later on. Anyway, then he thought that there are as many intersections from a given line to a curve as there are tangents that you can draw from a given point. And it turns out that this is false. Then again, I won't read the math, but we can discuss that later on. And Poncelet, for instance, found that the relation is not of equality, but that there's a more complicated relation. He found that what we call the class, so this number of tangent, is in fact m times m minus 1, where m is the number of intersections. So those two numbers are not equal. They're related by a more complex relation. But, Zeuthen would argue, this causes another problem to arise, in the sense that those transformations are supposed to be dual, therefore to return to their origin. And if you apply this transformation twice, you get an explosion of the degree, right? If you get, so here the second number is quadratic in the first one. So by operating further and further the same transformation, taking these two numbers, you get an explosion of the degree, and this is not good. So Zeuthen explains, in order to see that no contradiction arises from this fact, one must observe that the definition of generality is different depending on whether one speaks of a curve of a certain order or a curve of a certain class. The general property of a curve are those which belong to it, just as well as in particular cases, so long as the curve is regarded as a limit of a general curve, and so on. So the properties of a curve depend on the selection of a viewpoint on those curves, on a way of looking at them. And so, for instance, you can regard a given plane curve as either constituted of points or constituted of a bunch of tangents. You know, following a curve through its tangents, looking at its envelope, as we call it, you might have two competing definitions of the same object, which in most cases are interchangeable. But in fact, it results in cases where formulas become true in limit cases only from one or the other viewpoints. And so, so it came that Plücker found that a better way to go around those explosions of degree would be to add further terms which take into account singularities, so cusps or exceptional points on the curves in which the curve doesn't really behave smoothly but has weird properties. And he obtained those by looking at these alternative definitions, description via continuous motion of a point or via continuous motion of a tangent. I go very loosely on the mathematics here, but it doesn't really matter. What matters is that you have two modes of generations of curves, two ways of obtaining your object through different kinds of motions, different kinds of constructions, and from the combination of those viewpoints, Plücker obtains a final formula. Yeah. Okay. So, and essentially, the way to obtain this formula is to say that singularities, when they arise, cause a diminution of your number that is of a certain multiplicity, namely 2 and 3. Anyway. So the idea for Zeuthen from this well-known episode at the time in the history of geometry is that the formulas of Plücker and then before him Poncelet are only valid, are only useful in as much as the utterer, in this case, let's say the mathematical agent, keeps in mind its domain of validity. That is to say, the viewpoint on what geometrical objects are and how they are obtained, whether through, in this case, the two possible viewpoints being generation through motion of a point or through motion of a tangent. So the idea is that you have a strict, the necessity of a strict control of the use of formulas by the recollection of the origin, the genetic process through which the objects are constituted. And that the use of formulas, whether it be Poncelet's or Plücker's, must be kept in check by the recollection of this origin, of this genetic process. And not as a blind tool, not as something you can blindly plug in and use to compute numbers, but as something that you must always use critically with this origin in mind. But in fact, Zeuthen would go further and say that there is a form of geometrical knowledge that no formula can express, or rather, for which you can always complexify expressions in formula. That is to say, there is no hope to fully, once and for all, symbolize all geometrical knowledge. And he came to this conclusion through another case study in the history of algebraic geometry, to which this time he was more in which he was more involved as a contributor, as a mathematician. And so here's what he derived from this example. the exactness of a principle, so here in geometry, will depend on the formal statement that is given for it. And it may be difficult to find one statement which is subject to no objection and allows for no abuse. In fact, he would go later on to say that sometimes it's impossible to find such a formal statement that allows no objection, no abuse. But it will be enough to teach the method of which the principle is but the formally condensed version. So as to say, what really matters is not the formulas, but the method that corresponds to it. And this is what we must teach. I remind you that this is in the context of a textbook. And even he goes on to say, it is a matter of dialectics to decide whether a given principle allows for the impossible applications which some have used to establish its falsity, but at any rate, we can avoid such applications if we adjoin to the application of the method a true discussion of the way in which the cases that lead to issues are viewed as limit cases. And he says even this is what calculators do. When there's a difficult computation at hand, we must go back to such critical discussions. So why did he think that? So the case that he had in mind was the enumerative geometry of conics. So essentially, you might know that a conic is defined by 5 conditions. So for instance, a circle goes through 3 points. I mean, given 3 points, you have only one circle that goes through them. Yeah. For a conic, you need 5 points. And more generally, if you have 5 conditions of any kind, you'll get a finite number of solutions. So for instance, the typical case is if I give you 5 conics in blue, there's a finite number of conics in red that are tangent to them. And so this is a theory that Zeuthen was involved in from his dissertation onward. And he tells the story of the emergence of this discipline in the following way. In 1861, the French mathematician Ernest de Jonquière made the following contribution. He defined what he called a system of conics, which is the conics satisfying 4 conditions. So you need 4 conditions to fix your conics, so you take one fewer, which means that you have essentially a mobile conic. You can think of it as a 1-parameter family of conics. So you take your conic, and it's a continuous linear family of dimension 1. He said we define this number, the index mu of that system, as the number of conics that pass through an arbitrary fixed point. So this number characterizes the system perhaps in the same way as the degree of a curve characterizes the curve. And then his theory in 1861 resulted in the theorem for any other 5th condition Z, the number of conics in a system S that satisfies Z is of the form alpha mu. It's a simple expression where alpha is a number depending only on the condition and mu on the system, mu being that characteristic number. So in fact, this can be viewed as a Bézout result in P5. So P5 is the space that represents all plane conics. And you can view that as the expression of the degree of the intersection of a hypersurface and a curve. Won't get into the details. But anyway, you have a simple formula. Okay. The problem with this formula is that, as many readers immediately pointed out, is that it leads to the same sort of blowing up that Poncelet's formula had done. And so later on, and so it leads to blowing ups that were explained by the presence of degenerate conics. So the presence this is how people viewed degenerate conics at the time. So for instance, on the right, let's say that you have an ellipse that is being flattened. The limit case is that of, so first of all, you get a segment. So you get the segment between the 2 points, and then it explodes and becomes the 2 half lines that go outwards from the 2 points, and it turns back into a proper conic, namely that hyperbola. So you have 2 kinds of, in the classical view, you had 2 kinds of degenerate conics, that one with the 2 points on the line, and that one where you'd have 2 lines and 1. Anyway. And the presence of, people realized that the presence of those degenerate conics would lead de Jonquière's formula to blow up and provide and yield numbers that are way too big and that are obviously too big for what is expected in some cases. And so a few years later, Michel, with whom Zeuthen studied at that time, developed a slightly modified theory where he associated to the system not 1 but 2 numbers. So the one that associates, once again, to a system of conics, that number of conics that pass through a point, and the second number, the number of conics that touch a given straight line. So essentially, the dual number, we might say. And his theorem was that for any given condition Z, this time the number in the system of conics satisfying Z is slightly more complicated. You have the same term as before, but you have a second term. And this can also be viewed as a Bézout result. This is also a theorem that has great value. That would be the basis of the famous Schubert calculus. Anyway. And so here's how Zeuthen first described the relation between both results. The expression alpha mu due to de Jonquière falls under the same objections as many others before him, including Poncelet, because it refers exclusively to the representation of conics via punctual coordinates. So that is to say, it looks at conics only as objects that are generated through motions of a point. And so because it does so, it has the great advantage that it's quite easy to know what a particular case is. It has the benefit of using a very simple representation of objects, and that has its own epistemic merits. But it leads to the problem that the presence of double lines or degenerate conics explodes the numbers. So you have a trade-off between a formula that leads to many anomalies, but makes things pretty clear as to what you are actually counting. And then he goes on to say, well, Charles took into equal consideration the representation via points and lines. So Charles' addition of a second number, and so of a second term in this formula, has the advantage of taking into account conics not only as generated by a point, but also generated by tangent lines. So this makes the formula much better at dealing with problems with degenerate conics. So in that sense, it avoids many of the cases in which de Jonquière's formula is too big, but it makes it harder to understand exactly what the viewpoint on this degenerate conics is. And in fact, and this is the pivotal moment in Zeuthen's account, we would later find, so this is in 1876, that there are other kinds of degenerate conics. And so here, Zeuthen refers to an important memoir by the French mathematician Georges-Henri Alphen, who proved that there's a way to represent conics algebraically in which you can describe degenerate conics of yet further kinds. You remember in the Klein picture, you only had two different degenerate conics. Alphen found a way algebraically to construct a family of other degenerate conics, all of which behave differently with respect to this formula, all of which create further cases in which this time Charles' formula yields numbers that are too big. And this is the key problem. This time, one cannot hope to remedy the problem by adding, let's say, a third term in the addition. Like Charles solved de Jonquière's problem by adding a second term. This time, it doesn't work, Zeuthen says. One cannot remedy this weakness by adding another finite number of terms to the formula, because the number of Alphen's limit forms, so this degenerate conics, is infinite. So Alphen had constructed a way for any given, essentially he had found a way for any real numbers to associate to it a form of degenerate conics which behaves badly with regard to this formula. And so that means that there's no finite tweaking of the formula that would solve it once and for all. But of course, Zeuthen continues, this does not prevent us from solving each particular problem without any general expression. Zeuthen's idea was, well, the point of mathematical knowledge is not to be encompassed in these formulas, but rather in methods. And the method does not require a finite symbolic expression. One can teach you how to figure out in a given geometrical problem which of those limit forms arise, and then to compute. And the formula is just a tool. You will control it. You will find in each particular case exactly how much tweaking is needed, and you will work, in a more critical fashion. And so the idea being, as Zeuthen explains, we see through these examples that they who want to write a didactical treatise on geometry, meaning himself, have the obligation of imposing the just limits on the use of formulas. So formulas must be controlled. Maybe they must be put in check. They are not to be taken as autonomous tools for mathematical or pedagogical practice. And in fact, this is something that Zeuthen himself had written in a letter to Alphen a few years after this discovery. He says, you say that your theorem is more general than de Jonquière or Charles' theorem. I would rather say that your theorem is absolute, which is of a different kind, really. Because it's not that you've expanded the realm of applicability. It's not the same kind of move as from de Jonquière's formula to Charles. It's that you've once and for all transcended the problem and showed that it must be solved by other kinds of means. So essentially, how Zeuthen would frame this discovery in his lecture at the Royal Academy is that through this rather involved algebraic analysis, Halfand had revealed the existence of an infinite number of possible viewpoints on conics and their degenerate or special forms. And the integration of each of those perspectives or viewpoints always requires yet further terms to be added to the formula, so that there's no hope for a finite formula to encompass all cases. And the sort of absolute geometrical knowledge that one must strive for cannot be confined to equations. So the form of geometrical knowledge to be sought is not something that can be confined to equations. Equations have only a subordinary role. They must be kept under check by proper reasoning. So at this stage, you might wonder what this has to do with intuition. Why did Zeuthen use intuition, whereas here it seems to be purely a matter of methodology, and critical consideration of when the formulas are applicable or not? Well, to understand the connection to intuition, here I must say a few words about Bergson, or rather a kind of Bergsonism. So some of you might know this famous text, the Introduction à la métaphysique, in which Bergson, the first text in which Bergson really distinguishes between two ways of knowing a given thing, namely knowing through intuition and knowing through analysis. Sometimes he talks about intelligence versus instinct. And he for instance, at one point he takes the example of the knowledge of this quote is in French, of the knowledge of a city, and he says, well, you might take any number of photographs of a given city with atomic precision, if you will, and you might put all of those photographs together and organize them in a way that the streets that should be near to each other are also in your photos and so on. Yet this knowledge of the city that you have so obtained is still not as real, as true as the knowledge of someone who just walks into the city and experiences it from within and gets a good grasp on the lay of the land, how the city really feels, its organic unity, and so on. And more generally, in this text, he argues that so that intuition, which is essentially inhabiting the thing from within, yields a form of absolute knowledge that cannot be achieved with symbolic representations, which only lead partial knowledge. Symbolic here, once again, in this very broad sense. So that begs the question, however, we might say, well, the absolute knowledge that Zeuthen had described in Halfand's sort of explosion of the problem of enumerated conics, sure, it has this quality of encompassing an infinity of viewpoints and of doing away with mechanical uses of symbols, whereas but still, how can one really hope to connect mathematical practice of the highest order with Bergson's outright anti-mathematical philosophy? It seems like an uneasy fit to really try to apply Bergson's theory of intuition to that kind of mathematical thinking. And here one must stress the fact that, in fact, what Zeuthen knew of Bergson and how he pictured Bergson's philosophy was not at all through encounters with the primary text, but rather through the intermediary of Harald Høvding, here on the left, who was also in the drawing of the Academy, a Danish philosopher, and theologian and psychologist, who, among other things, gave very popular lectures on the history of philosophy in Copenhagen, including a set of lectures on Bergson, to which Zeuthen was present. And Høvding, who was by all means a proponent of Bergsonian philosophy, nonetheless introduced Bergson's philosophy with a rather strong Kantian twist. He was also a strong proponent of Kant, and he sort of read Bergson through Kant in a very interesting manner. And his major point of disagreement with Bergson, which he exposed in his lectures from 1913, so a year before Zeuthen made his Bergsonian coming out, was that unlike Bergson, he thought that intelligence, or analysis, was a necessary intermediary in the obtention of true intuitive knowledge. Intelligence, he says, and its way of thought, are but an obstacle in our ascent towards intuition, our supreme goal. Had intelligence not been awakened, and had it not done its work, development would never have passed beyond the pure instinct which points the way immediately and exclusively in a single direction. So in the sort of long history of how mankind developed knowledge, a base instinct needs intelligence and so analysis, so mechanical apprehension of the world, to push it forward essentially, and in the end, hopefully, reach proper intuitive knowledge of the sort that Bergson desired. And in so doing, Höfding distinguished 3 levels of intuition, which kind of work as a 3-stage Kantian model, and which Zeuthen made his own. The first one is that of concrete intuition. As soon as I open my eyes, I perceive a sensible image which forms a certain totality, so an indiscriminate totality. In memory arise interior facts as spontaneous images of totality, and in imagination there is a new creation of such images, and so on. From the first moment, there is no very clear distinction between sensation, memory, and imagination. They become mixed up and bound up with each other. So this very unrefined, brute form of intuition that also corresponds both to perhaps the development of a certain person's intelligence, but also as this sort of long-term history of mankind that are always mixed up in these philosophies. Then arises an analytical intuition, whereby the immediate comprehension of the difference or identity between 2 images appears, and it is an act of thought which takes place in comparisons. So this is where we develop knowledge of relations. We relate those brute and refined totalities, intuitive totalities to one another, and in fact, this is this is one of the first forms of intellect appearing in this story. And finally, so intellect is then able to grasp those analytical totalities and work on them, symbolize them, represent them through symbolic devices, and compute with them essentially. And there, only then can this synthetic or absolute intuition appear, which is the utmost form of knowledge that one should strive for, in which the immediate perception of a connection or a totality, which may be acquired by going through a series or a group of members of parts, if one has a certain comprehension of their mutual relations. So in this form of intuition, we are able to see all of those chairs, understand how one could descend through intelligence to represent them as chairs. We can decompose them, but we can also grasp them as a totality of chairs. We are able to navigate between the totality and its parts. We have a full, fluid knowledge and understanding of what is present to our intuition. And so this rather abstract theory was in fact developed on the basis of many examples from various sciences, which perhaps clarify the stages of these 3 stages. So for instance, at one point, Höfding relies on Friedrich Max Müller's theory of linguistic formations, his lectures on science of language, as one example of those 3 stages of intuition. So for instance, Müller's theory of language was that at the childhood of humanity, we develop languages in which words are merely roots, primitive sounds that are inseparable. So we make one sound to express one idea, and one cannot separate them. There's a one-to-one relation between primitive sounds and ideas. Then these roots are coalesced 2 by 2 by words. So for instance, we have the sound for meat and the sound for broth, and we combine them to distinguish between different kinds of broth. So this would be the operation in which analysis or intelligence comes into play. This is something that we do. That this is essentially a sort of symbolic practice, as they would say. So this is a conscious, active, intellectual process. And then languages develop, and you get to the way that Müller would describe languages like German of his time, whereby roots are so deeply intertwined that words are these complex totalities that the expert philologist is still able to decompose and relate back to these roots, and he's able, in a given word, to retrace this historical process. But nonetheless, for the average user, we have totalities that work in a very complex fashion, and so so this kind of language is used in an intuitive fashion, although the possibility to go back to this analytical decomposition is still available to certain experts. So you see the going from sort of a base intuition to a higher form of intuition through intelligence, through symbols, and the possibility of going back whenever needed, at least for the expert. And in fact, Höfding also used that to talk about things like geometry, but I will skip that. Okay, and for this, and so now the question is, how did Zeuthen use the declaration, and how did he relate that to geometry? And for that, I want to briefly discuss his very last book. So this is a set of lectures on the history of geometry, which he published in 1917, although they were given over the course of several years, which is sort of his last word on the history of geometry, in which he wants to describe what he calls the emergence of geometry as a rational science. That is to say, the passage of geometry as something instinctive and unscientific to a rational science, and sort of a reform. So his basic idea is that a lot of the geometrical knowledge that we find, for instance, in the elements, was already known, at least as a basic level, by many other people before Euclid. But Euclid was at the end point of a reform of this knowledge, which finally turned it rational and scientific. And Plato plays a big role in that story, but I won't get into that. And key to this narrative is the idea that what Euclid really achieved is turning this previously acquired knowledge into a whole, so a logical whole, but a whole nonetheless. It's as a holistic totality, wherein we can equally account for hypotheses and conclusions. So the idea being that we can navigate between the axioms, the definitions, and the theorems, and we can also go back from the theorems to understand why hypotheses are needed, why axioms are the good ones, etc. So stressing not the axiomatic nature of the work, but rather the holistic totality of the holistic nature of the elements. And in writing this long story of the birth of geometry as a science, he makes use of two different kinds of knowledge: psychology, and in particular Gestalt psychology. So, for instance, Edgar Rubin's, another Danish scientist, Edgar Rubin's dissertation from 1915, in which this well-known grand figure experiment is first exposed. So you all know this picture where you can see two faces or a vase, depending on how you look at it. And ethnography. Ethnography being a science that emerged in Germany, but also in countries near Germany in the 1880s, and which was a very popular pastime among the educated elites. And in the context of Copenhagen in particular, a big attraction was artifacts from Greenland. And in particular, those objects on the left, which are wooden maps of the coast, of parts of the coast of Greenland that you use with your hands, tactile maps, so to speak, which attracted a great deal of attention in Copenhagen in the 1890s. Why are those things interesting for Zeuthen? Because they point to the origins of geometrical knowledge before it was turned into a rational science. That is to say, both we can use psychological experiments and this ethnographic artifact to understand how spatial intuition before the intervention of intelligence operated. That is to say, on the three stages of Höfding, those kinds of documents, those kinds of sources tell us what the first stage of intuition, the first kind of intuition in geometry might look like. And in fact, this is something that you might know in Felix Klein's infamous lecture on intuition in Evanston, where he distinguished between Aryan and Semitic intuitions. He's very much appealing to the same idea. So the very racist treatment of artifacts from Greenland is something that is not restricted to Zeuthen. So he uses those sources to construct a story in which he describes this, what he regards as a global phenomenon, intuitive sensations, for instance. This is just one example of similarity, especially in the context of those maps where you have a similarity between what you feel on these wooden objects and the coast, the shape of the coast. Intuitive sensations of similarity motivate effort to solve certain problems, e.g., for example, the ratio between circumference and diameter of a circle. And at the very end point, through the intervention of intelligence, which stabilizes for instance, this sensation of similarity into symbols, into words, and makes it liable to be used under symbolic means. At the very end point, you get things like Book 5 of the Elements, wherein the theory of proportions becomes fully codified, and that's the result of this big reform. So all knowledge is placed into a new logical system. And in fact, there are many interesting things many interesting relations between Zuyten's philosophical views and his historiographical positions, for instance, on geometrical algebra. And also the way that he highlights Euclid as a foreigner of intuitive mathematics rather than axiomatics is quite interesting. But anyway. However, says Euclid, even in the Elements, the immediate primordial sensation of similarity lingers on. Independent definitions for similarity of segments and polygons are given, yet one same word is provided for these cases, which supposedly points to the presence of this origin story. And Greek readers did not bat an eye. This was only possible because they all partook in this primordial intuitive sensation. And later on, this initial sensation grows distant. And so, for instance, when Apollonius gathers all definitions of similarity of conics into one common property of the lattice rectum, we need no longer maintain this link to our sort of common intuitive past, and science has grown purely rational and independent from this first level. So you see that Zeuthen is reconceptualizing a long history of geometry through those kinds of Höfding and Bergsonian schemes. And in fact, and this will be, and then I will conclude, it's along those lines that he would reconceptualize all kinds of geometrical knowledge. So for instance, describing what it means to understand a formula in geometry or otherwise, he would conclude the following. A formula is entirely composed of symbols. They who know the symbols may apply this formula to such individual cases as are obtained by giving determined numerical values to the symbols of magnitude. The wholly new investigations in which this formula may be useful, however, may only be carried out by one who possesses an intuitive overview which regroups in one all the particulars of the formula, preferably with the addition of a recollection of the role played by these particulars in its genesis. So going back to those formulas, for instance, de Jonquière, Charles' formulas, and the problems with it. What does it mean to master a formula? It means, first, and of course, on a very base level, it means being able to plug particular numbers in it and compute with it. That's obviously the base requirement. But that's not it. It also, to use it in theoretical research in mathematics, and especially to use it in new investigations, in new problems, one must also possess this sort of intuitive understanding, this third level in Höfding's scheme, this refined intuition of the formula, an intuition in which we know not only how to compute with the formula, but also all the possible particular cases which may arise in or against it. For instance, all of the degenerate cases that Halfett had pointed out. And so we must master all the possible particular cases that may arise, in what way they contradict or cause anomalies in the formula, and we must have this absolute overview, which is also a critical overview of all the ways in which the formula might have to be tweaked in order to be applicable and used in computations. And key part at the end, which is also something that Höfding emphasizes, this is particularly good if we know how those particulars were involved in the genesis of the formula. So knowing the intuitive origins of the symbolic form is something that is also a requisite. Okay, so what have we seen? So the way I try to describe Zeuthen's position, especially towards the end of his life, is obviously it's a thoroughly anti-mechanistic view on the formation of mathematical objects and knowledge. So the objects of mathematics emerge through this flow of geometrical experience, both on the historical level, but also on an individual level. And I stress that this is a theory that accounts for both the formation of objects and knowledge, the two being intimately linked. Once again, this problem. So holistic intuition, this last level of intuition, is viewed clearly as the highest form of mathematical knowledge, or knowledge in general. and it's the result of a long historical process and something that we must learn as well individually. In a sense, what Zeuthen is trying to tell us is that to become a geometer is not to know formulas and theorems, but it's first and foremost to learn how to see figures, and to learn how to see a conic not just as a drawing on a blackboard or on a sheet of paper, but as something that can be obtained through various processes, something that we can look at in different ways, and being able to navigate between these different ways of looking at the figure. So really the training of a gaze is how Zeuthen conceptualizes geometrical teaching. Finally, not finally, but furthermore, a non-trivial role in acquiring sight intuition is left to symbols. So symbols are not done away with. They are still very much in use, and in fact, obviously you see symbols in Zeuthen's textbooks, but they are always to be kept under the control of intuition. And in fact, Zeuthen makes the claim that proper rigor and mathematical certainty is only achieved when this intuitive control is maintained. So rigor is not left to symbols, but very much to intuition. And in fact, symbols cannot, and no amount of symbolic sophistication can secure rigor and certainty. Only intuition can. So this is this together. These things are quite close to what Das and Galison in their history of objectivity call trained judgment. Anyway. And lastly, one might also describe that as an agent-centered philosophy mathematical practice. We might remember his description of how one calculates, how it's really a description of mathematical practice that is really focused on what it is to actually use formulas, to actually compute with symbols, to actually look at figures. And it's a philosophy that is very much in communication with an array of contemporary sciences, advances in Gestalt psychology, in ethnography, in linguistics. All of them contribute to this view of intuition and mathematical practice. And so I think this case really calls for an opening up of the history of philosophy and mathematics to those other histories, without which one cannot really hope to understand what Zeuthen and his contemporaries in Copenhagen are doing at the time. And I think I'll stop here. Thank you.
Thank you very much. It was very rich, so I have lots of questions, but I'll try with, I start with some clarificatory questions. I think you answered in your last slide, because I was struck by your use of control, the way you talked about formulas that needs to be controlled by intuition. Just a comment, but I would like you to say more about that, because it's usually the other way around. And so I wanted you to comment a bit more on that. But one thing that struck me also at the beginning, I don't know if it's your translation, is that you mentioned the utterer as the mathematical agent.
Yeah.
And so also on that, I would like to push you to say more about that, because it has to do with the role of language, but uttering is normally related to speech. And so, but symbols, what about the materiality of symbols? The fact that these were written formulas, why the utter? Maybe it's a translation issue, but so these are two kind of related questions.
Yeah, so I mean, sorry, this is so clear. So this is my synthesis, so this is not a translation, this is very much my thumb. I didn't have speech in mind, sorry. I thought I could get away with using it generally as expressing something, the person who or the group of people, the group of persons who express something. I very much had in mind textual utterances as a possibility, so sorry, that's confusing. On control, so control is of course, that's not a term that Zeuthen uses, but or rather, he doesn't really have a very consistent vocabulary to describe these things. One might keep in mind that his philosophizing on these issues is something that he does late in his life and in a variety of settings and in variety of audiences. So the vocabulary is not as consistent as one might wish. He's not a professional philosopher. So in a way, what I'm doing is trying also to get out, to sort of carve out a general statement from very various sources. So, but control in a way that for instance, he describes quite in details how if one wants to, even in, let's say we want to do algebraic computation, we want to solve an algebraic problems, and the problems go quite complicated. Zoyden says it'll be good to use not just one method, but maybe two competing methods to check that they are in an agreement, right? And so he says those kinds of strategies are routinely used by algebraists because they know that even though the algebraic method, the symbolic method is valid, there's obviously always the possibility of individual errors or of suddenly having stumbled upon an exception case that is not easy to control. And so we use alternative methods. We have these strategies that we deploy in order to control the validity of what we've done. And he says, well, the same is true of geometry, except that it becomes so hard to know whether or not we have stumbled upon an exception case that symbols will not help us. In the case of singularities, whether it's the singularities of a curve or of a system, the control cannot come from equations because there is no way to construct a symbolic system in which the symbols do the work for us of determining whether or not we are in a valid case or an exceptional case. And so the control must come from having mastered the totality of possible conics or curves or whatever, and having fully understand how they morph into one another. So the idea of being cognizant of how they turn into one another and what are the transitions, the transition forms. So that kind of view of how things move into one another is really important. And so I call that control because it's really the idea of being from sort of an upper perspective that symbols do not provide. And certainly the theme of the word in Danish that he uses for those things is it's essentially the same word as in German Sicherheit, so security, safety perhaps. And so in order so the idea being that symbols do not provide that sort of safety. We are never safe if we are just using symbols. We need that. So that's what I call control.
Yeah, because it looks like it means being sure that they have a meaning, that they have an intuitive meaning or something like that.
So the symbols have a meaning which relates to how we look at objects being formed. So, for instance, curves as a set of points and so on, and they occasionally lose meaning, and we must control when exactly it happens that they lose meaning, and that the symbols cannot provide. Yeah.
Thank you. I think I have a follow-up to this, what you just said, and it relates to the slide where there's a quotation from Höfting, I think, from a letter.
A letter?
Yeah. It's about the dispensability of intelligence.
Yes. This one?
Exactly. So in the end, you have to overcome, so to speak. I mean, calculus, computation is certainly a very helpful mean, but in the end point is a kind of intuitive knowledge, you said. Yeah. But one could argue the contrary around. It's just you need intuition as long as your calculus is not general enough. If you've reached the really general point of view, you will be able to build in all restrictions on domain in which a calculus is useful. You can build it into the calculus such that you don't need any intuition anymore to have a working calculus. You won't do that kind of paradoxical thing that they did in the 19th century. And I'm thinking here about a real position, namely Whitehead's position with universal algebra, and then also with his later work on projective and descriptive geometry, where I think one of the ideas was that to actually arrive at such a general point of view that you wouldn't need intuition to help control your symbolism, because it was already, everything was built in. So my question is, did Zoyden react to this? Or if he didn't, how do you think one could react from this opposite point of view of Zoyden?
So he didn't react to Whitehead specifically, but he reacted, for instance, to people like Peano, or mostly to contemporary geometers interested in axiomatics, who always referred in a certain way to Euclid, and so he's very much opposed to everything you just said radically, and he thinks that it's in general not possible to achieve that kind of autonomous calculus in which, for two reasons. The first one is that the people who actually do the computations, or whether it's actual computations or logical derivations, whatever, the people actually do that, mathematicians, mathematically minded humans, let's say, and those people might make mistakes however good the calculus is, the possibility of mistakes still remain, because especially mistakes not only in the sense of I wrote down 1 whereas it should be a 2, but also mistakes in the sense of I used the formula slightly beyond its applicability range, which are more subtle mistakes, which arise not through negligence but through a lack of overview, exactly, precisely. So he would totally disagree with the possibility of achieving that, at least for meaningful theories in geometry and so on. It's also important to remember that the geometry he has in mind, those kinds of algebraic geometries, are not yet, when he's writing, turned into algebraic systems that have no issues. Really, he's talking about advanced geometrical theories in which it's not so clear how one might go about turning them into algebraic mechanisms in which intuition is. That would be achieved a few years after he was dead, one might argue. So, so he's really has in mind that kind of cutting-edge geometry in which it's not so clear how one could do that. But of course, what he has in mind is the people like Peano, Hilbert, and that's what he wants to describe as a dangerous way of understanding what mathematical thinking is about, and something that we might very well do it to symbolize Euclid's axioms, and we might perhaps achieve what you described in that case, but not in more substantial theories. At least that's. I'm describing his views. Don't ascribe me anything. I have no opinions. But
okay. So you wouldn't say that later developments in algebraic geometry somehow showed Sutton's position to be wrong? I think,
for instance, I think there's an argument to be made that what Bill Thurston describes in his famous paper in the early 90s, maybe 92, 93, on proof and progress in mathematics, echoes some of Sutton's concerns, namely the idea that what really matters in mathematics, and especially in mathematical communication, is understanding that what really goes on in the transmission of knowledge in mathematical talks or papers and so on is understanding, and that it's something that cannot be put purely into formal garb. That's something that also requires drawings. Thurston was famous for including lots of drawings and using fuzzy arguments that nonetheless won him a Fields Medal, so it can't have been too bad. So I think there are more contemporary, more modern echoes of those views, which are quite, at least convince me that there is something to be said about it. Although the competing views equally are. So I don't think it's clear. I don't think there's a clear-cut case to be made that his views are completely obsolete once, intersection theory was developed. I think it would be you could make the case against that convincingly, although it would require more work. But
Okay, Andrea.
Thanks. Thanks. I just wanted to ask, you mentioned on your conclusion slide the notion of flux, so a flow. So for flux for Bergson was very important, and he linked it to this idea that we could know things through the medium of film in ways that we didn't know them before film. So the dynamicism of images flowing together gave us a perception that was natural even in ordinary life. And I wonder if Zeuthen ever comments on this as a way of thinking about mathematics, because in particular the case study you looked at involving degenerate conics, you could think of each of those degenerates as developing through a dynamic change from one to another. And so this image from Bergson could be quite useful there. I wonder if he did that or not.
Absolutely. So he did not specifically comment on film, but the language of things, being transformed and it's stressing how looking at singularities of curves not just as a property or a point, but really as something that appears through a transformation, through a continuous transformation, something that really, or curves moving into one another, systems of curves transforming into one another. That kind of continuous description of the transformation of an object is key to not only his late philosophical pronouncement, but in fact, really in his mathematical, this is quite significant, something I can't really show in a few words, but in his mathematical papers, it's really a key practice of his to describe vividly, really, the flow of mathematical objects. And in the textbook, it's really a key practice. So, I think the comparison works, even though he doesn't really specifically comment on this, as far as I know. Thank you.
Okay, Jemma, Lorenat.
Thank you, and thank you for your talk. I'm so happy I'm speaking after you. So I have two related questions. One is that you're primarily drawing on Zuyten's later writings, but then he's referring back to the history of mathematics in the early 19th century. And he had a remarkably long career. I didn't realize that he had lived so long. And I wondered if you saw any evolution in his position on intuition and symbols over the course of his career. And then relatedly, I was hoping you could say a few more words about something you mentioned in the introduction about Zuyten's position perhaps not sitting well with our view of the history of mathematics in the early 20th century. So, so both of those, please.
Okay, so on the first one, well, first of all, the reconceptualization of his geometrical practice at the end, both because he wanted to write a textbook, and also in order to make it available to a broader public. For instance, the vocabulary of intuition really only appears through the contact with Höffding. Before that, he uses only words of method, reasoning, those kinds of words. So intuition is added to this view of mathematical practice because he becomes aware of at least a certain kind of Bergsalism. However, I would say that in his mathematical text, for instance, in his classic papers on what we call birational transformations and on the conservation of the genus and so on, there already so those are papers in the 1880s and 90s, we see him shy away from, he will give a formula and then he will say, well, what really matters is I'm not going to prove the formula, I'm going to prove how the apparition of certain singularities modify that other numbers, and I will describe to you a method through which you can understand how those changes affect those quantities or those properties. And so you already find very much in his practice when he's writing for the Mathematische Annalen or like mathematical journals, not at all, for his peers, you already find very concrete instances of that commitment. So I think here very much it's a case where the words and the theorization of this intuition is quite late and is very much tied to a specific encounter, but the mathematical practice underlying it is something that he had developed very concretely whilst working as a mathematician, and not at all, regarding how Zuyten sits with the big philosophies of mathematics at that time. One thing that I find quite interesting is that, for instance, I think not many people who defend intuition at that time go as far as to claim that intuition is really the path to certainty. I think this is quite a strong, even if you look at obviously someone like Poincaré, who's one of the big names you associate with a defense of intuition, he would never go as far, I think, as Zuyten in ascribing to intuition this rigor, this role of rigor that symbols could not provide. And of course, the other big name associated to intuition, namely Brouwer, has a view of intuition that is also critical of symbolic representations and paper mathematics and so on, as they call it. But it's a view that is way more mystical and almost solipsistic, whereas Zuyten's view of intuition is really also oriented towards teaching, towards opening to other people the possibility of inhabiting these transformations, and certainly the connection with that Bergsonian philosophy and those cultural markers in psychology and so on is very much, it's very peculiar. So I think it's very much possible to separate Zeuthen and to identify Zeuthen as a very original position, whilst at the same time acknowledging that some of those ideas circulated very much. So the connection with Klein is very interesting, and Klein also was someone who held intuition in high regard. Although I think none of them went really as far and made so much with this notion and the idea of transformation. So I think he's quite an interesting author in that regard. Although I'd be happy to be proven wrong, but yeah, thank you.
Thank you.
Yes.
A last question, maybe by Gerhard for the lunch break.
Thank you very much. Yes, I cannot understand the second sentence here.
Yes.
Holistic intuition is the highest form of mathematical knowledge, result of a long process and distinct from immediate intuition. Okay, this is distinct. Okay. How to see figures properly?
Yeah,
I cannot understand it.
The idea
what
is
it means. I mean,
so the idea
it is conceptual.
Yeah, no, but so the idea is that if you're in possession of that absolute form of intuition, and you see a curve on the blackboard, you understand at once that the curve might have been obtained and might be conceived of in various ways. So you know how to see the figure not just as that particular drawing, but as an element of many families, as something that could have been obtained through the deformation of many other kinds of objects. And so you are able to navigate those mobile objects in a way that lets you know what properties, what formulas are applicable to it. You are able to know how to descend to the level of symbols and computations in a safe manner. And it's really about knowing how. Essentially, it's a certain way of dealing with intuitive objects, figures, in a way that not only achieves the same level of generality and abstraction as symbolic theories, as algebraic theories, and so on, but also to understand how they came about, where the intuitive object arose in the development of a theory, in the solution of a problem. So
Okay, but this is always conceptual learning. I see now what is. I cannot see, but what means intuition in this sense. I learn conceptually, naturally. I'm familiar with what I learned. My concept, different concepts, okay. But why this intuition?
Because it doesn't resort to symbols.
Because?
Because it does not rely on symbols. The big distinction is whether or not you are using symbols. Here, symbols being, of course, not only species, not only letters or so on, but you are not using words that are to be manipulated through mechanical rules. So when you're using the word curve or singularity, you're not just using them under the rule of mechanical rules.
It's not mechanical, but conceptual. Okay, good.
I have no argument against concept. I'll take conceptual. I have no issue with concepts. But yeah.
Okay, I think we can thank Nicolas again.
Thank you.
So there's a bunch of sandwiches on the back. There must be some version options, so just check, let's see if there's a sign or something. And we resume it at 1:30, I think. Okay. Yeah, no problem. Yeah, so it's 1:40, so we're going to start for our afternoon session. And so the first speaker is Jemma Lorenat, and she's going to talk about anxiety, decide, and intuition, so geometrical figures around 1900. The floor is yours.
Okay, thank you. Is this on? All right. Oh, yeah, I can tell that it's on. All right. Just plug in my microphone. Get it there. I just don't want to trip on it. All right. Thank you. Thank you for the invitation to speak. Thank you all for being here. I'm excited to share this work. This is part of a larger, actually a larger book project I'm working on about how the local environment at Bryn Mawr College shaped mathematical practices there around 1900. I'll talk more about that in a little bit. So I'm going to be spending the next 45 minutes or so talking about pictures and some quotes to introduce that. So this is a nice one from Alice in Wonderland. What is the use of a book, thought Alice, without pictures or conversations? And bringing this into the realm of geometry, because I'm going to be talking about mathematics. So Charlotte Angus Scott, who's one of the mathematicians I'll be talking about this afternoon, in the introduction to a later textbook wrote, although the proofs of analytical geometry are purely algebraic with no dependence on any diagram, yet it is well to make a practice of representing conditions and results in a diagram. The diagram itself proves nothing, but it shows us what we have proved, and indeed in many cases it helps us to see precisely what it is that we wish to prove. So I think this is a useful way to think about visual aids in geometry. And then to speak more specifically about anxiety, poetry is useful here. So this is from W.H. Auden's poem, The Age of Anxiety. Do reflections yield reliable knowledge, especially given that mirrors invert? So this idea of the problem of representation. So this talk will proceed in 3 parts. I'm first going to talk about anxiety around figures and how that connects to a larger anxiety about modern mathematics at the end of the 19th century, and then strategies for coping with this anxiety, and then finally conclusions and further questions. So I don't know if this is visible. This is from Jurassic Park 2. And this is actually exactly the phenomena I want to be talking about. So we have Tyrannosaurus Rex in the rearview mirror. I don't think this is still a phenomenon. I think this is like a feature that only exists in cars from the 1990s. I don't have a car. Do mirrors still give this warning? Objects in mirror closer than they appear? Is this familiar to anyone? Okay, so I'm going to be talking precisely about the precise ways in which figures mislead us and text that can explain that to us. And this is also a great picture because it captures a situation I think we will all be feeling anxious in if this is what we encountered in our car. So to set the stage for anxiety. So I started to think about anxiety in figures from looking at the work of historian Jeremy Gray, who's written about anxiety in modern mathematics for over 20 years. So in Formalisms and Intuitions, his chapter in the Symbolic Universe, he speaks about signs of the anxiety that of non-Euclidean geometry generated run like fissures through late 19th century geometry. And a slightly longer exposition of this same theme is in his book, Plato's Ghost. He has a section on anxiety, and he writes about to speak of rigorous separation and a willingness to abandon part of what was hitherto one's own, but has become dangerous, is to use the classic language of anxiety. So this relationship between the disassociations in modern mathematics and this feeling of this unmoored feeling of being anxious. And you see very similar language in writing about figures, specifically
in this same time period, so late 19th, early 20th century. Actually, this is even earlier. So Jakob Steiner, in his textbook on geometry, is talking about the use of visual aids, and going back to this, the abandonment of visual aids even though you've been using them. So he's specifically talking in a pedagogical context. So when he's moving into discussing figures in 3 dimensions, he says in the following considerations, the structures and their different connections, because they no longer line the plane, cannot easily be represented through drawings or figures. Overall stereometric considerations are, in my opinion, only properly understood if they are intuited purely, without any sensory media, only through the inner. I left this in German because it's like power of representation, maybe, but sometimes it's actually translated as intuition into English, which I think is an issue when we talk about intuition, is a variety of translations of different words, especially from German into English. So this leaving aside of figures because they actually interfere with developing your own power of representation. So having the visual aid being inhibiting the ability to develop the mind's power. And this is taken to a further extreme in the work of von Stout a couple decades later, where he famously, in his book on the geometry of position, has no figures whatsoever, and again justifies this with respect to pedagogical benefits. So saying that students should begin from general considerations and learn to make in different ways from geometrical structures and to practice his ability to intuit. And again, figures actually inhibiting the development of the ability to intuit. Then now actually getting to the end of the 19th century, 4 different reasons, again, removing this problem with the figure. So these are not, at this point, not so much pedagogical worries about the figure, but again, finding that the figure is perhaps not appropriate in geometry. So Pasch famously claiming the theorem is only truly demonstrated if the proof is completely independent of the figure. And then similarly in Hilbert, one could avoid using figures. We will not do this. We will use figures often, but we will never rely on them. So this language, to me, resonates very much with this language of anxiety of figures introducing too much within geometry and there being a problem with them and one needing to do something about it. So having very quickly established this claim that there is anxiousness in the use of figures at the end of the 19th century, I now want to look at some of the strategies adopted at this time to cope with this anxiety. And so I'll do this in 3 parts, looking at avoidance, and then global strategies and local strategies. And I'll talk a bit more about what I mean by local strategies when I get there. So avoidance was not actually a very common strategy. I mentioned von Stout famously had no figures in his text, but this was weird and noted. So this was not, so although there was clearly some anxiety, not using figures at all was not the common way of dealing with it. So von Staut's text was only, in the 19th century, only translated once into Italian by Mario Pieri at the request of Corrado Segre. So Segre has an introduction to this translation, and he's saying that von Stout wanted his book to have no figures, studying it without using them or making them alone as one reads. Perhaps the reader will make more effort to conceive the most difficult figures, but the geometric conception will become stronger. So he's according with von Staut's vision of not using figures, but he's noting it as something that a reader would not expect. And similarly, Pieri also points out that the reader is going to be surprised that a book that's supposed to be aimed at youth wouldn't have any illustrative plates. But then he goes on to say, it seemed to us better advice to be faithful to the concept of the author who published his work without figures and always declared himself against the idea of introducing them, assessing that the young man should become accustomed on the one hand to conceiving of geometric shapes without any mechanical aid, and on the other hand to directing his attention not to a single case, but to a set of cases for each proposition. So figures specifically inhibiting your inner conception, but also the particularity of figures being a problem. And that, I think, is actually what carries on to the late 19th century, this problem with figures being particular and individual. But avoidance was not a very common strategy. Von Stout did it, not really anyone else. And in fact, although Pasch and Hilbert warn against the use of figures. I see this as more of a global strategy. They have a statement in their text saying, don't rely on figures, and then they use figures. And this is also adopted by Veblen and Young in their projective geometry. So this is the text where they have a figure, and then in this footnote here, they explain how you're supposed to use them. So it's a global warning against figures. So this is how they can be used. They would be regarded as a concrete representation of our science, in which the undefined points and lines of the science are represented by points and lines of ordinary Euclidean geometry. Their function is not merely to exhibit one of the many possible concrete representations, but also to help keep in mind the various relations in question. In using them, however, great care must be exercised not to use any properties of such figures that are not formal logical consequences of the assumptions. So it's a pretty general idea of like what you shouldn't use, but the reader's sort of expected to know what to do, right? It's not quite clear what exactly is one can take away from a figure's general warning. And then this is not dissimilar. I mean, this is now moving into topology, but Poincaré's famous quote about geometry as the art of reasoning well from badly drawn figures, and then he explains what he means precisely. These figures, they are not to deceive us, must satisfy certain conditions. The proportions may be grossly altered, but the relative positions of the different parts must not be upset. So again, this general explanation of what you can and cannot take away from figures that are given in these texts. So the advantage of these global strategies is they can be quite brief. You can say in a couple sentences, and then you have your whole book where you use figures and you expect the reader to know what to do with them. But I'm going to spend most of my talk spending time with local strategies, which end up being much more involved. And I mean local in at least 3 senses. So first, local as in specific warnings about figures that are tied to individual figures. So what precisely in this precise figure can you take away from it? Like the picture of the Tyrannosaurus Rex, right? It's actually closer than it looks. Secondly, I mean local with respect to a certain area of mathematics. So thank you, Nicolas, for talking about singularities. I'm going to talk about singularities. Now you're all experts. And so I want to look specifically in the resolution of singularities on algebraic curves. How are the figures introduced, and what exactly can be read from those figures? And then in the third sense of local, I'm going to be looking at a specific time and place. So I'm going to be looking at Bryn Mawr College outside of Philadelphia around the year 1900, so at the turn of the century. How did the figure practices from research in singularities migrate to other areas of mathematics? You'll see some of the same ways in which figures can and cannot be read. And then, yes, I know, I will talk about intuition, and then lastly, looking at what actually are figures. So looking at singularities, from as early as 1750, there is this sense, and I think this came out in Nicolas' talk, that what we perceive visually is not always what's there. So in Kramer's text on algebraic curves, he points out, referring to figure 114, that the inflection at A will no longer appear, although it really exists in an infinitely small space, and is perceivable by analysis, whose sight, if we dare to speak like this, is more piercing than ours, so our human sight. It is easy to see that inflections are alternately visible and invisible. So inflections, he has 2 different kinds of inflections. Inflections that you can see, that if you were to think about inflection, well, I'll show you. That one, you know, the one that you typically think of, but then there's this other kind of inflection that analytically is an inflection, but is not visibly an inflection. And so he's explaining precisely this lack of sight correspondence to the given figures. And this is adopted by Salmon and Cayley in their treatise on higher plane curves. They're pointing to this distinction, points at which the tangent meets the curve in an odd number of consecutive points. Points of visible inflection are distinguished from these points of undulation, which do not, to the eye, differ from ordinary points on the curve. So this precise way in which the eye is misleading, but then the author is carefully explaining to you that what you see is not what you get. And this then becomes, as geometers continue to study compound singularities, so the coincidence of multiple singularities at the same point, these same practices continue with explaining how to read figures. So here I want to specifically point out, so it says the case 3, that's the case on the far right, scarcely differs visibly from an ordinary point in the curve, but when the figure is drawn accurately, there is a certain sharpness of bend at the singular point. And then in a later case B, there is in like manner a real branch which comes to pass through an acnode. To the eye, the singular point does not appear to differ from any other point on the curve. So this attention to specific points that look one way but are really another, and the ways the figure is wrong intentionally. The study of singularities, so one path along the way of studying singularities is to consider the resolution of singularities and their penultimate form, by which is meant the moment before you have all these singularities coalescing in the same point, what did the curve look like the moment before that? And so this is a research program that really begins with Cayley in the mid-19th century, this pulling apart of these points, and then often a graphical representation of what did the curve look like before this moment of coalescence. And so here in this annex figure, this is from Cayley's text in the Encyclopedia Britannica, it represents the singularities as on the point of coalescing. So this is quite an interesting visual aid in that you have a curve being considered as an object in time and then going back in time and showing some moment. But of course, it's by its very construction somewhat imprecise how far back in time you go, and being able to show these features as distinct. So if we go, like you could always get closer and closer until it's impossible to see these different points about to meet. So you have this balance between wanting to show what it will look like in the end when it does coalesce, but then also wanting to show the distinct features just prior to coalescence. And so this then leads to certain drawing opportunities that Cayley takes advantage of. For instance, here you can see points C and E, and he says for greater distinctness, the points C and E are there drawn nearly instead of actually coincident. So this precise language explaining how he's purposely made an adjustment to the figure to illuminate a certain property that's not actually correct. So Cayley's research on singularities led to a question about penultimate forms in general. So using Cayley's equations as well as Plücker's equations on the relationship between the kinds of singularities in a higher singularity led to these numerical values. But then this raised a question as to whether these numerical values that corresponded to which kinds of singularities were meeting at a point, there was a question of did that mean anything, or were these just 4 numbers? So was there actually a geometrical meaning equivalent to these numbers of double points, double tangents, cusps, and inflections? And this question of does there exist a penultimate form in which all these singularities exist, distinct from one another, but infinitely close together? So Smith posed this question in 1876, which was then taken up by a variety of mathematicians. Brill and Halfman work on this. Although they're not so much concerned with the graphical resolution, and it seems to be more of a British and American preoccupation to study these graphical penultimate forms. So this is a very little known Cambridge mathematician, Walter Percy Workman, who's continuing this question posed by Smith to see whether the Cayley equivalent numbers, these are these values, are proved to have more than a mere arithmetical significance. And so he claims that Brill and Halfman show that there exists a penultimate form, which by continuous variation of its coefficients, the ultimate form containing the higher singularity in question results. Both Brill and Halfman give deformation processes by which the penultimate can be obtained from the ultimate. So there's an analytical process that you can find this penultimate form, find that there actually is a geometric correspondence to these numbers, and then a tradition arises of showing the penultimate form. So you can see in figures 38C and 38B, C is the actual curve with the higher order singularity, and then P shows the penultimate form right before that happens. And so with this flexibility in drawing, where you're drawing a curve before it reaches its final form, this seems to allow a certain degree of freedom of manipulating the figure to show distinctness. So in this same text, Workman, for instance, with 33C, decides to scale the ordinates 20 times larger than the abscissa. And so this flexibility of looking at a curve over time then privileges distinctness versus correspondence to the algebraic actuality. And similarly, Charlotte Angus Scott, also Cambridge-trained mathematician working in the same research area, resolving higher singularities of plane curves, begins to show these penultimate and final forms. So here, she's introducing her work in the graphical analysis of higher singularities and trying to show the compound singularities in these penultimate forms. So to summarize these different ways in which figures are manipulated and then explicitly given instructions as how they're manipulated, we can see a change of scale and proportions to reveal small features, so extending vertically or horizontally. The use of the penultimate form to show the composition of singularities, and then this deformation as continuous variation of the coefficients in the curve's equation to show the path of a curve at a singularity. So how a curve is approaching the singularity and then leaving it, so you can actually follow along in a certain direction over time at these points in which in the final form you really can't see what's going on. So now I want to turn to figure practices at Bryn Mawr College. So as I mentioned, Charlotte Scott was the chair of the department at Bryn Mawr College, so she started the math department there. And her early research is on the resolution of singularities, so she has quite a lot of experience with these specific figure practices where you can manipulate the figures. And I want to show first what that looks like with the study of singularities, but then how it migrated into other areas of geometrical and topological research. So here, and you'll often see these instructions on looking at figures in footnotes and small places. So here, figures 23 through 26, for the sake of distinctness, the tangents are more widely separated than is justified by the construction, and the two branches that cross and recross at 1, 2, 3, etc. are drawn with inflections, as the scale is too small to keep them distinct in any other way. So this privileging of distinctness, visual distinctness, introduces certain properties of the curves that are not real properties of the curves, like adding tangents. And then to further specify this idea of deformation, Scott actually uses displacement instead of deformation. But here in figure 26 on the top, this is how well, maybe if you have better sight than I do, you can see how the curve is going in and out at that point. But I'm assuming probably not, right? It's very hard to follow once we enter the singularity where we're exiting from. And it's happening at certain places. But if you displace slightly the components of the point, then now they're separate enough that you can actually follow those lines. So this role of displacement allows you to see the path of the curve over time. And so you have certain visual properties being privileged over others, even though the curve never actually will look like this. This is just to be able to follow with your eye the course of the curve. And these practices lead to increasingly schematic illustrations. So here, in another paper on singularities, there's a few different visual processes being employed to show different features of the curve. So this is actually all one thing. But so at A, you see that there's this point O, which is a singularity, and then it's displaced in this unlettered curve below him. So now you can see the course of the curve at that singularity below it. So it's just to show how it's going in and out. Similarly, on the top right, the part of the figure labeled B, that's simply the path of the point P. And this is to actually enumerate how many times the direction of P is changing. So it's reoriented from being more vertical to being more horizontal, which you can see by following the arrows, with the purpose of simply being able to count, okay, it reverses directions twice. And so this is both separated and reoriented in a different way to illustrate certain properties of the curve. And then part C, this is actually another picture of O over on the left. And here we can see the change in the direction of the tangent line OP. We have the tangents going, you have two tangents where you have a change in direction. So again, a reorientation, a separation to show certain features of a curve which are not actually representational features, but other features belonging to the curve that can be shown in a pictorial form. And so these specific uses and manipulations of the figure are then adopted by Scott's students and exported to different areas of mathematics beyond the study of singularities and their penultimate forms. So here, the copy of these figures, unfortunately, I wasn't able to get a better copy of them, so it's a little hard to see, but it's probably okay because they're just diagrammatic and they don't give the actual appearance, but they simply indicate the sides on which the different curves touch. So this is her first PhD student, Isabel Madison, is working on differential equations, and she provides these figures, but she describes them as only diagrammatic because they're not representational. They're just showing positionality between certain features of the curve. Similarly, Ruth Gentry, working on a classification of plane quartic curves, actually building off the work of Zeuthen, gives these figures, and she points out that the figures she's giving are only rough drawings intended to illustrate the salient features of the types. Some or all of the ovals would probably be impossible with the remainder of the figure as drawn. It is inaccuracy of the figure either accidental or serving to make the bay readily apparent. By bay, she simply means actually, well, similarly to the geographic formation, sort of when the curve has like a bay-like shape. So she's on purpose introducing inaccuracies in the figure to show certain properties, privileging some over others. She goes on to say that although the figures are only approximate, still a certain measure of accuracy has been aimed at. The bays are faced in the right direction with reference to other circuits. The sharpness of contour of an embayed circuit in the neighborhood of an oval is intentional, and goes on to illustrate or elaborate specific things that you can and cannot read from the figures, specific visual properties that can be drawn by looking at them and others that are mistaken. And then, for instance, she ends by saying, a certain approach to symmetry is often observable in the figures. This is, of course, not an essential feature. So this is really an elaboration of Poincaré's claim of what can and cannot be drawn from these badly drawn figures. These are figures that are drawn badly on purpose with precise features manipulated and then explained quite clearly. Similarly, this is another graduate student of Scott's who was working on the arrangement of real branches of plane algebraic curves, so working now in topology, and she explains that her figures, again, as we saw earlier, they're added inflections in order to bring the figures within the scale of the paper, and the figures represent the distribution of the ovals of the curves accurately only with respect to the number in different regions of the plane. So there's these inaccuracies in the figures, and they become even more schematic in this later drawing, where really now she's only showing enumerative properties of the ovals, that some are internal and some are external, and then how many are each. But they're not, they're representational in a sense, but really moving away from that quality of figures. And as a last example, and maybe the most extreme, so this is a paper on knot theory from 1918. And here, another Bryn Mawr graduate student is using a really interesting figurative property in which she's used white discs to cover features of the knots that are not essential. So they're shown and then they're blocked. And this is, there's some number of crossings occurring in the circle, but it doesn't matter for the purposes of this explanation what's going on in the circle, so it's blocked. And it's just to show what's happening above and below when you have what she calls a reversible tangle, but essentially just doing this. I hope that gesture makes sense. Okay, some knots. And then what's happening inside the white circle is just staying constant, so it doesn't need to be represented. So this is quite an interesting introduction of a visual feature that's then explained what's going on here. And to my knowledge, Heinzmann's the first person to use this technique, but then it's adopted by later knot theorists in the mid-20th century. So we can see an even longer list of processes for manipulating figures in precise ways and explaining how that's happening. So the first three I already discussed in the context of the resolution of singularities, but then we also have the adding of inflections for greater distinctness, symmetries that are written to be inessential, rounding or sharpening of curves to emphasize critical points, redrawing and reorienting components to show combinatorial properties, and even hiding features of a curve within the figure itself. So the figure being obscuring features on purpose. And I'm not saying that this is the first place in which these are introduced, but what I find quite striking about these set of figures is the explicit annotations that accompany the figures, explaining exactly what you can and cannot see about the figures and what you can take away from them. So this guiding of the reader into the practice of the ways in which figures can be representational and not representational. So what does this have to do with intuition? So I want to continue to look at some of the practices at Bryn Mawr to elaborate the relationship between these figure drawing practices and writing about figures and intuition. And this brings us to Klein, something that was already mentioned earlier today. So Madison is talking about curves which cover an area of the plane, and she goes through an example that shows there are certain curves which cover an area of the plane and lead us to correct the idea given us by the, quote, naive intuition that a curve is a mere stroke without breadth drawn on a plane. So there's a certain kind of intuition, naive intuition, which can lead to error. Similarly, Scott, in a paper on the transformation of plane algebraic curves, she introduces this idea of compartments, which are just these different numbered areas of the plane divided up by certain curves. And she explains that these compartments serve, in the first instance, as a convenient symbolism for the expression of algebraic results that present themselves. But as the laws formulating the arrangement of the compartments are gradually established, the compartments themselves can be used in the proofs without impairing the rigor of the argument. The compartment idea is intended to appeal not to naive intuition, but to refined intuition. So these two different kinds of intuition, naive intuition being, well, neither of them are explained yet, but refined intuition being something that's being developed. And so these compartments being a tool that can then be used with refined intuition. This distinction between naive and refined intuition is from Klein's Evanson-Cloquin lectures. These were mentioned earlier today. So he distinguishes between naive and refined intuition and says, in my opinion, the root of the matter lies in the fact that the naive intuition is not exact, while the refined intuition is not properly intuition at all, but arises through the logical development from axioms considered as perfectly exact. And his figure on the right is an example of naive intuition. And so this distinction between these two different kinds of intuition that Klein introduces in this context is adopted not only by those working in the American context, which is where he gives this lecture, but also to take a well-known example, the illustrations of Koch, the Koch snowflakes, he also borrows the expression of naive intuition from Klein from this same text. So here, the curve I found in which forms a principal object of the following study is defined by geometric instructions, sufficiently simple, I believe, for everyone to be able to sense already through naive intuition the impossibility of a determined tangent. So this division between these two kinds of intuition circulated fairly widely after Klein's introduction of it in the early 1890s as two kinds of intuition. And what I find particularly interesting about this intuition is it's not quite clear, and maybe the answer is both, that you are refining your intuition, or if the figures are speaking to your refined intuition. So it's a relationship that's perhaps working in two directions. And this recalls, going back to Steiner, this idea of developing your power of representation. And so he says, whoever would seek to circumvent this effort by other means will likely not do well. In that the power of representation, instead of becoming healthy, strong, and active, will fall into darker, more difficult views. So perhaps we can think about this as refining figures to appeal to the intuition, and figures that are refining the intuition. So this process of perhaps the intuition itself is being refined, or the figures are being refined so that they appeal to some intuition. And I think that reciprocity is quite interesting here with this idea of refinement. So as Scott is increasingly precisely changing figures in a way to emphasize certain non-representational qualities of them, her idea of what a figure is and can be seems to also be changing. So in her 1894 textbook, she's following Plücker, defines a figure in any space as generated by a moving element coinciding successively with certain of the ultimate atoms of the space according to some law of selection. And this is really in accordance with Plücker's work on algebraic curves from 1839, thinking about a figure as being generated simultaneously by tangent lines and points in forming a curve. But she offers a somewhat different conception around 1900 after interacting with Hilbert's work. So Scott was present at the International Congress of Mathematicians in Paris in 1900 and then wrote a report on this for the Bulletin of the American Mathematical Society. It's a really great report. I highly recommend it. And in it, she reports on Hilbert's famous sharing of the mathematical problems there. And so here she's synthesizing Hilbert and says, the proper treatment of any problem depends on 1, a complete system of axioms by means of which the conceptions are defined, and 2, a system of symbols appropriate to the conceptions with which the problem deals. Thus, a demonstration by means of geometrical symbols is as legitimate as an arithmetical one, provided that the axioms on which it is based are perfectly understood. So this idea of geometrical symbols, and then to look more precisely at what Hilbert says, because this is just Scott's version of Hilbert. So this is a translation from 1902. So the geometrical figures are signs or mnemonic symbols of space intuition and are used as such by all mathematicians. The arithmetical symbols are written diagrams, and the geometrical figures are graphic formulas. And no mathematician could spare these graphic formulas any more than in calculation, the insertion and removal of parentheses, or the use of other analytical signs. So this equivalence, or near equivalence, between symbols and figures, or figures as a kind of symbol. And Scott here is really just synthesizing Hilbert, but then at least by 1906, she's invoking this same concept with apparent agreement with it, that the figures used in geometry are symbols, not representations. They're in the same category as the symbols of algebra, and she quotes Hilbert on that point. So same quote as before, slightly later. So she seems to believe that figures, at least by 1906, that figures are symbols within geometry. And although she is quoting Hilbert here, this actually also goes back to Plücker, who Scott really saw herself in following in the same sort of philosophical understanding of mathematics. So this is from his earlier text in 1828, where he basically argues that, that the symbols of algebra are figures. One only needs to consider that we never lose sight of the given figures, namely those symbols that represent them. So the algebraic equations are the figures for Plücker, at least in this work. However, in 1828, with Plücker's work, he's calling the symbols of algebra figures to borrow the evidential weight of figures for analytical geometry. So against a critique that analytical geometry loses sight of the figure, Plücker says, no, the equations, the algebraic equations of the curves are the figures. So he's using the evidential weight of figures to give credence to the use of symbols. But in 1900, you could say that the balance of trade has shifted somewhat in that figures are gaining the semantic flexibility of symbols. So instead of saying that symbols and figures are the same in order to gain power for symbols, now the idea is that saying figures and symbols are the same actually gives more flexibility to the figures. But one could argue if something is lost. So this is from Brill's work on the resolution of singularities, asking if Cayley's equations only have a kind of symbolic meaning as being perhaps not enough. So perhaps in calling figures symbols, there's something lost as well as something gained, one could argue. So to draw some conclusions, so I first want to return to anxiety. So if we take this idea of anxiety and mathematics seriously, then it's perhaps useful to look at the psychological literature. So according to current clinical practices and evidence, avoidance is not good for anxiety. So if you're anxious about figures, not using them probably will not solve your problem. And in fact, so digging into this a little bit deeper, this is like ridiculous armchair psychology. I spent a few hours on this, so like this is not medical advice. But one of the 9 social causes of depression is a disconnection from meaningful work, and it's solved by reconnecting to meaningful work. And so if mathematical anxiety is caused by disconnection from meaning, then could precise use of distorted figures help to reconnect and alleviate this anxiety? So in fact, if there is this anxiousness about figures saying too much or too little, then explaining very precisely what you can take from them could let you use them with confidence and feel better about yourself and your use of figures. I think this use of figures also recognizes the plasticity of both figure and intuition in this context. So despite the fact that figures may be anxiety-producing, they're still used by Hilbert and Posch, and in part because figures are cheap, and they're fast, and they're mnemonic, and they're malleable, right? They have all these properties that we want, even if you don't consider them reliable. They have these other attributes. And if you state precisely what can and cannot be read in a figure, this helps elucidate Poincaré's badly drawn figures in a way that he generically states, but for someone just entering mathematical practice, to see precisely how figures can be used is quite useful. And some features then can be accurate and reliable, but training through prior education, or in the cases I've been showing you, through the accompanying text is required. So saying exactly in what ways figures can be accurate and reliable. And similarly, intuition can then be considered as a developable faculty, the training of the intuition to be able to intuit things in a reliable way. So the use of these figures in the work of Scott, in the work of her students, and then more generally in the resolution of singularities, this blurs this distinction between figures and symbols. So if mathematicians and philosophers today see a clear difference between figures and symbols in mathematics, this is certainly not true for all mathematicians and philosophers circa 1900. There's this conflation and renegotiation between them, and I see this lack of boundaries as in fact fruitful and not just messy. This intertwining between figures and symbols ends up being quite useful as a practice. And one might even see these annotated figures where exactly what is representational is made quite explicit as mark of an evolution or metamorphosis from illustrations into more systematic diagrams, as to something that's purely representational to something that's more schematic, and that the accompanying language is really showing that evolving process. Hence this drawing of evolution. That's the resonance there. It's not just random. And then to return to this idea of mirrors, just some final questions. To what extent are the text and figure practices at Bryn Mawr local or regional? Are they only acceptable for certain journals, applied in other areas of mathematics, sustained over time, driven by technological limitations? So I see this actually as quite an interesting continued area of study to get a sense of in what context are we seeing this writing of this annotation about figures and how they can be used. This is just this second part is something I'm just beginning, but further questions in that area. So thank you so much, and happy to answer any questions.
Questions? Don't book too much.
Okay. Well, thank you very much. This was really interesting, and I was reminded of secondary literature on Aristotle's use of letters in his syllogistics, and I was thinking whether maybe there was like the opposite process coming from language, colloquial Greek, to something that becomes more and more schematized. I mean, already the form of the affirmative judgment is already like it's not real Greek, and if you translate it into English or German or French, it's always like this very strange way of formulating an affirmative judgment. And then you can go further. You can use, for example, capital letters for the notions that are predicated, and you will use the A, E, I, O notation. You can really substitute the syllogism by a diagram of letters, and I think there are quite similar processes involved in getting from, let's say, natural language to symbolism than what you described. So in a certain way, it's just wrong to think that there really is a device. Symbolism is just a way to get to this kind of schematic figure that you can get from the other side when you come from the geometrical figure side. And historically speaking, this is what Aristotle did in a certain way, because his predecessors were geometrists using letters together with figures. So it was. And I was wondering what you would say about this possible other direction from natural language to some sort of schematic symbolism.
Yeah, I would love for you to share the secondary literature, because I'm not as familiar with that, but I think that's precisely right in that there is training involved in these ways of seeing things, and sometimes it's made explicit and sometimes it's anticipated to be known to the readership. And so these moments in which it is transitioning, and so you really need to take great care in explaining what can precisely be seen in either direction, I think are quite illuminating, at least as a historian, to sort of glimpse what can become implicit or tacit knowledge.
So you think that in the end these figures could really become some sort of symbolism, or have they become actually a sort of...
I don't know what happened after, so there's a point in which my knowledge ends, which is like 100 years ago. But they are clearly becoming more, but I do see that they are becoming more schematic and more, and less representational, and I hesitate to call them more symbolic because of this long-standing tradition of equating them as already being symbolic, but certainly less representational and more showing increasingly abstract relationships. Yeah.
Thanks. Varaya?
Thank you very much. I have a comment and a question. The comment is about the case of the hiding features of the curve, which I find very interesting, because as you said, it's a moment of negotiation between something more iconic, let's say, and symbolic. And this is a case in which I would say that today you would expect something like, I don't know, a symbol like ... or something like this to cover the feet. And there you have like something that is really, really covering the picture. And so it's a comment, it's just a comment, but I never found it, and it's very interesting. And the other question that it's probably off topic and probably a spoiler for tomorrow, but since the names are the same, so what about models? And do they make you anxious as figures or less? And were they in the picture here? Because I just happened to read the things with the same names about France and Europe, and so I was wondering what was happening with them. But maybe it's off topic, so.
No, that's good. Actually, so a comment on your comment, Conway also uses these white circles. I think he got them from Heinzmann, but he doesn't cite her work, but he has like an L inside of them. I can share it with you, but it was really cool to see, because it's a weird thing to see in a drawing, and so then seeing it again later was like, it must be from the same source. I think in some ways models are less problematic than figures because they're expensive. And so you don't just make a model casually like you can with a figure. And so there's something distinct there in actually the material processes that makes models have to be more intentional because of their dimensionality. And so when in this time period models are being made, at least in mathematics, there seems to be more of a purposeness to make them accurately because of the labor and expense. And so to make an inaccurate model in mathematics, if you can make an accurate model, it would be preferred in a way. But then, of course, sometimes it's not possible to get accuracy on all things, and then you are similarly having that trade-off of what features do you want to privilege. So I think there might still be some language about anxiety because they're visual, but I think there's less everyday interaction with them because of the labor involved.
Thank you.
Matthew Inglis.
Thank you. That was super interesting. I want to ask you a bit about your use of the word anxiety, and I'm just kind of curious as, like, to what extent you really mean, anxiety in the I guess medical sense. There's lots of things it feels to me that I'm nervous about the accuracy of, or the potential to be misleading, which I wouldn't want to say I'm anxious about. And then you do, if you ever work with students who have maths anxiety, they start sweating and their heart rate goes up. I mean, presumably, Maurice, Pash didn't start sweating when he saw diagram. Oh, did he? I don't know. So I'm just curious as to exactly what you mean by anxiety.
Yeah, so I'm really just working from Jeremy Gray's work because he talks about modern mathematics as inducing anxiety. So in a way, I'm being casual about it. I don't think I'm speaking about it in a diagnostic sense. I agree with you. I don't think Pasha is necessarily sweating, although I don't think we'll ever know, so maybe. But really, and also even W.H. Auden in his poem on the age of anxiety, it's clearly not in contemporary diagnostic sense of anxiety. So specifically about, I think the features that are raised by anxiety that I wanted to highlight are this disassociation from meaning, and perhaps nervousness is more appropriate than, but the feeling that the discomfort perhaps is even more accurate with this disassociation from meaning, and figures importing meaning that maybe we don't want to import, but this discomfort with what figures might be providing that we don't want to have provided in mathematics. But then I thought I would just dig into the contemporary definition of anxiety a little bit more to see if these coping strategies with figures had any resonance with contemporary clinical practices. And from that I just took away, well, avoidance is not beneficial, and then that some sort of connection is a possibly useful path.
Andrew Anna.
Thanks, Jemma. I wanted to ask, we talk about intuition, we're often thinking about the word having a kind of ocular resonance, that there's, Descartes speaks of the mind's eye, for instance, as being operative here. In the cases that you're looking at in this geometrical practice, at least at first, this ocular image seems really called for, because we are talking about figures as being that which we see. Mm-hmm. But one of the things you're describing is a kind of shiftiness here with respect to the kind of sliding away from the ocular image towards something, for instance, symbolic, where symbolism isn't purely visual, but also involves some other kind of mode of thinking, right? So if we think of symbolist art, there's a fact in which parts of a piece of art stand for. They have some sort of relationship, but maybe not representational in any precise sense. And I think I was struck by your quote from Kramer, which I think brought this out pretty well, right? In which the ocular image he wants to to bend to even accept being able to see by means of analysis, by mathematical analysis, features of what's going on. So I wonder if you would want to say in the end, is some of the anxiety that you're describing here, anxiety about the ocular image associated with either geometrical or mathematical thinking or even thinking whatsoever, a recognition that our conception of thinking needs to be less centered on the eye and more on other features of thought?
I'll offer a tentative response because I'm not totally sure. But what I think is interesting is while these figures are becoming less representational, they are still being perceived by the eye, as are the math. I mean, so the mode of perception is still largely through the eye, although one could probably convert some of the symbolism into something that was delivered through a different sense. I think that's absolutely possible. It's just not being done in this context. And so some of these more schematic figures are showing relationships, but in a visual way still, right? So showing the relationship between, or you're seeing the course of the curve. So it's not representational of how the curve looks, but it is still ocular. So I think it's maybe both narrower and more general in that it's really the representational quality that's seen as the problem versus it being ocular.
Gerhard?
It's really related to the last question. I don't understand correctly your thesis, as you said, mathematicians and philosophers of today clearly distinguished between figures and symbols. Naturally, what do you presuppose? You presuppose that there are figures are given as a pure data. Without a theory, you can see it. Then it's a figure. No, then I see only curves in a literal sense, but no figures. So surely there must be surely a difference between perceptual representation and conceptual representation, but not so between figures and symbols. I think this is.
I more meant if some mathematicians and philosophers see it, but not all. I agree. I don't think that distinction is made universally today at all. But there are instances of figures and symbols being treated quite distinctly. And I was trying to more emphasize the latter point, that distinction doesn't seem to strongly exist in this earlier time period. But yes, I absolutely agree that they're not treated as completely distinct by all mathematicians and philosophers today. Thank you for clarifying.
Any other questions?
It's actually a follow-up to the question before. How about accounting differently for this process of becoming more and more diagrammatic figures? Maybe you could, because I think you said something of the sort, well, you need additional explanation conventions to understand the figure. But maybe the initial figure needs also a lot of convention already. It's just something that we learn very early on, and so it doesn't need to be explained. And then what looks like additional convention is more like a shift in convention, that you say, well, you have to read the figure differently, but then it's not so much that it becomes, in a way, more conventional or less representational. It's that you just change the language, so to speak. You change the conventions rather than adding further conventions. That might be one, and then you could say, well, writing is just as figurative as drawing. It's just other conventions. It's and it's more continuum than some sort of. Yeah.
I agree that absolutely the perception of figures. There are conventions, yes. But I would still say that this is an addition of conventions because it's not removing the prior conventions of seeing figures in geometric practices, at least. It's just increasing conventions of things that can be changed. But I would probably need to start with a list of the prior conventions to then actually compare that and see. But I think no matter what it is, what's really interesting is the explicitness of them in these research articles, whereas the earlier set of conventions for geometric figures are being taught so early on that it's actually quite hard to find any writing about what those are. But presumably somewhere there are some.
Mm-hmm. Thanks.
Yeah, I have a questions about the idea of like training intuition, because so when you're talking about training intuition, I mean, also like following some of the questions you said here, are we actually should we have an expertise on how to use the intuition, or should we actually train the intuition itself? Because it seems like intuition, the same as perception, is that it's just some kind of like an input. Like there's a certain number of things we can spatially imagine. As you said, there's limitations in terms of like figuring out how these curves, where do they come out of the singularity points. It seems like you could train as much as you want. I mean, you can be a bit better, but we see like there are clearly limitations of our cognition for doing these kind of things. So when people are talking about train intuition, I'm always wondering what it means. So is it like training intuitions at this low level things, or is it really like training how to use our intuition? In which case you connect to this idea of conventions and understanding how things are used, what you can do, what you cannot do, etc. I don't know if you have something to say about that.
Yeah, I think it's ambiguous for these mathematicians when they're talking about refining intuition or developing this practice of mental representation, whether that is actually changing something about intuition or training the intuition. I don't think it's clear precisely. I mean, I think even in this idea of refined intuition, it's not clear if the objects are appealing to something that is refined intuition, or if that you're refining intuition in order to perceive these objects. So I think there's actually quite a lot of interesting ambiguity there as to in what role intuition is entering and what is meant by intuition. Is it something that can be trained to do things, or are you actually training it? Yes, I think that's two distinct things. I don't think it's made clear by these mathematicians precisely.
Maybe there's some connection between all these debates and philosophy of mind, the relation between cognition and perceptions, interrelation between the two. I think that could be relevant for all these kind of things. Yeah. I mean, the same idea that we're talking about like conceptual representations and intuitive representations. I think we are always talking about like these more general problems that is identified there. Any other questions? Yeah. Jessie?
So this resonated quite a bit. I remember as a graduate student, my professor in community of algebra would draw these figures on the board. And I remember us grad students getting in the elevator afterwards, and I felt discomfort because I was like, we have no idea what the heck he's drawing. He's like, I'm trying to give you my intuition, and we were like, we have no idea, like, because the meaning was dissociated, and I think we did feel some discomfort there. And so I'm wondering, maybe have you found instances, instead of maybe training people how to use particular figures developed by mathematicians, maybe helping train students on how to create their own figures? And did you find any instances of positive affect when people were developing figures?
So I haven't answered that question, although it's not precisely your question, but at least with respect to the training of how to create these geometrical figures, that was also a very common practice at Bryn Mawr. So everyone was required to take classes in curve tracing. And so there was a concrete material practice of making the figures, and there are texts that show how do you work from an equation to generate a figure. Now those are then going to be not schematic figures necessarily, or less schematic, right? These added conventions aren't there, but explicitly how do you work from an equation to something that now we would use the computer to do. But so that's absolutely happening in the same place, and so there is a strong tradition in this school of learning how to create figures, and then perhaps because of this strong training, then learning how to break those conventions or stretch them as well. Oh, and positive affect. Could you explain what you mean by that a little bit more?
Yeah, so like anxiety, discomfort, this is more negative affect. So when I think about positive affect, just feelings of joy, happiness, comfort. Do you see any like positive emotions showing up when people are developing their figures?
Not that I can think of, but now I really want to look for that. That'd be amazing. Yeah, I don't think there's a lot of finding positive affect in mathematical texts. It's few and far between, I find. But I'll look out for it, and I'll get back to you if I can find any of that, because that would be quite nice.
Okay. If there's not any more questions, I think we're on time, so we can thank Jemma again. So we go for 10-minute breaks, and then we will reconvene.
Should I turn this off then?
Not off,
Okay.
mute.
Oh, just here.
Okay, so the next talk is by Christophe Eckes from the University of Lorenat. So we didn't say too much about the founding and the setting, but we can do more tomorrow morning in the opening. But this event is like a giant enterprise with Nancy, so we're both involved in both organizations of like the workshop that we had in Nancy in May and this one. So many of the four of us is me, Bruno, Gerhard, and Andy. And so this is why the Liège people talk in Nancy, the Nancy people talk in Liège. So Christophe is part of the Nancy people, and is going to talk today about Coutura and the role of rational intuition on the idea of numbers, magnitude, and order. The floor is yours.
So thank you very much for the invitation. So the philosopher and scientist by training, Louis Coutura. Oh, what happened here? So he defended his main and his secondary thesis at the Sorbonne in June 1894. His main thesis, entitled De l'infini mathématique, was published in 1896. It is divided into two main parts. First, a part devoted to the generalization, several generalizations of the concept of number, and then a second part articulating two ideas, the idea of number and the idea of magnitude. And these two parts are augmented by a series of appendices covering several topics, in particular the general theory of complex numbers. Okay, so at the end of book 1 of part 1 of his doctoral thesis, Coutura offers a critique of the so-called arithmetic generalization of the idea of number, arguing in particular that the new numbers successively introduced in arithmetic are presented as pure symbols, originally devoid of meaning, and take on value and meaning only through the relations to which they are subjected. Before adding, but the operations themselves are formally defined as abstract combinations according to certain formulas. Coutura deems this arithmetic theory inadequate due to its formalistic and artificial character. It is inspired, this arithmetical construction of numbers, by Jules Tannery's Introduction à la théorie des fonctions d'une variable, which Coutura completes and simplifies to suit a non-specialist audience. Coutura then goes on to spell out his critique of this arithmetical approach. Now, this usefulness of the various kinds of numbers cannot appear in the theory we have set out, because the analytical method does not account for their rational origin. It posits symbols a priori, but does not explain or justify them. By presenting them as pure being of reason, it strips them of any raison d'être, thus emptied of their concrete content, cut off from all communication with reality, and as if deratiated from the field of intuition, where they had grown. Arithmetical concepts undoubtedly offer a perfection of form, a sharpness of outline, and a transparency eminently favorable to their analytical study. But on the other hand, they are inert and dried up like the flowers in an herbarium, and we can no longer understand either their birth or their development, for they lack to the sap that nourished them and kept them alive. The quotation from Coutura continues as follows. In short, the formalist theory of numbers succeeds in purifying arithmetical concepts only by stripping them of any intrinsic meaning. Their natural genesis is replaced by a conventional and tactical genesis, a kind of arbitrary creation ex nihilo. It proceeds, as it were, by coup d'état. To qualify this method in two words, it is logical, but it is not rational. So this purely logical and analytical conception of numbers is considered as arbitrary and meaningless in Coutura's doctoral thesis. Accordingly, Coutura intends to oppose a logical order, cut off from all intuition, and a rational order, which is visibly based on an intuitive content whose contours will be specified in the second part of his doctoral thesis. 9 years after this book, Coutura published Les Principes de Mathématiques, directly inspired by Bertrand Russell's Principles of Mathematics, and accompanied by an appendix on Kant's philosophy of mathematics. This appendix reproduces an article by Couturat published in the Revue de Métaphysique et de Morale in 1904 for the century of Kant's death. With this article, Couturat sets himself up as the gravedigger of the philosophy of mathematics inherited from Kant. Okay, indeed, he celebrates Kant's death. So Couturat's 1905 work and its appendix document his support for a logicist conception of a substantial part of mathematics. Such a conception appears most clearly in the conclusion of the Principe des Mathématiques. Thus, pure mathematics is defined both by its form and by its matter. By its form, which is a set of implications conforming to the principles of logic. By its matter, which is a set of definitions containing only terms of logic. It is therefore understandable that, from the point of view of form, it is identical to logic, and that, from the point of view of matter, it is merely a special domain within the field of application of logic. This explains why it has the abstract and formal character of logic while remaining distinct from it and subordinate to it. So, in this book, this 1905 book, he argues that we can reconstruct a great part of pure mathematics without the slightest appeal to intuition. Pure mathematics is subordinate to logic in both form and content. Pure mathematics consists of concepts and truth, to which we can attribute a universal and necessary value inherited from the laws of logic. Such arguments show to what extent Couturat embraced Russell's logicism. Okay. So at first glance, we will be dealing with two Couturats. A first Couturat in 1896, who intends to thoroughly reform Kant's philosophy of mathematics while refusing to reduce mathematical sciences to a so-called logical order. A second Couturat relies on Russell's principles of mathematics to lead a true anti-Kantian crusade. So what would be the right frameworks? Historical, scientific, and philosophical frameworks for understanding such a contrast between these two Couturats. In particular, a term-by-term comparison at most allows us to identify such a contrast, but not to eliminate its meaning. So, first point, Couturat's interventions are part of a particularly dense reception of Kant's philosophy of mathematics in France during the second half of the 19th century. So this is the first big problem. See Charles Braverman's thesis on that topic. Second point, most of Couturat's contributions are welcomed in the Revue de Métaphysique et de Morale. So we will have to refer precisely to this journal. Third point, Couturat is also a scientist by training, who shows himself to be very attentive in his reflections to contemporary mathematical developments. So there must be changes explained by some mathematical or logical developments between his doctoral thesis and his 1905 book. And as contrasting as they are, these two books share a certain number of philosophical questions that should be made perfectly explicit. So, some assumptions. First assumption of mine, the reading of Kant proposed by Couturat as early as 1896 is part of the opposition, then very structuring in France, between a rationalist conception and an empiricist conception of mathematics. And seen from this perspective, these two books by Couturat will be different variants of a rationalist conception of mathematics. Second assumption, Couturat's philosophical thesis, as well as their evolution, must be analyzed in light of the controversies in which he is involved within the Revue de Métaphysique et de Morale, and one cannot underestimate the polemical tone of several of his articles. Third point, the transformations at work in Couturat's philosophical reflections on mathematics can be explained by his reading of certain scientific texts. I can give here one example. Couturat is well informed about the recent developments in formal logic, the foundations of mathematics, or even the development of group theory. As an example, Peano is absolutely not quoted in Coutura's doctoral thesis. On the contrary, this reference is absolutely central in Peano's book from 1905. And fourth point, fourth assumption, two philosophical problems are systematically addressed by Coutura between 1896 and 1905. What are the ideas that serve as the foundation of the mathematical sciences? What are the links between those ideas? Of course, there are several unpublished texts by Coutura that have been recently discovered. First of all, of course, is scientific correspondence, which has been progressively published, but also Coutura's lecture notes, which are very interesting during the period 1897-1899 at the University of Caen. Oliver Schlaut published some of these lecture courses, and they can make sense of the differences between these two Couturas. There are some transitions that are perceptible by referring to these lecture courses. Second point, of course, there is now an abundant literature on Coutura. I can quote here the works of Clara Silvia Roero and Erika Luciano documenting Coutura's essential role in the propagation of Peano's mathematical logic in France. Contributions by Stéphane Soulier, Jules-Henri Grébert, and Charles Braverman to the devoted to the early years of the Revue de Métaphysique et de Morale, and also comments by Dominique Pradel on Coutura's doctoral thesis, Sébastien Gandon on les principes de mathématiques, and also by Gerhard Heinzmann on the Coutura Poincaré's controversies, etc. So in the first part of my presentation, I will give a kind of contextualization of Kant's legacy in Coutura's main thesis. Then I will try to interpret his main thesis from the standpoint of a rationalism whose aim is to found pure mathematics on the idea of magnitude as a rational intuition. Third part, a philosophical reflection on the ideas on which mathematical sciences are based, which is borrowed from Antoine-Augustin Cournot. And fourth part, a logicism closely related to a growing emphasis of the idea of order in Coutura's later writings on mathematical sciences. So first part. The bibliography accompanying Coutura's main thesis contains only a very few philosophical references. Cournot, of course, but also Husserl, Charles Renouvier, who was one of the first promoters of Kant's philosophy, and especially Kant's philosophy of mathematics in France during the second half of the 19th century. All other references quoted by Cournot in his bibliography are mathematical books, manuals, articles covering the following themes: arithmetic and elementary algebra, function theory and infinitesimal calculus, construction of imaginary quantities, projective geometry, construction of real numbers, set theory. So this bibliography is symptomatic of one of Coutura's aims, that is, building a philosophy from the mathematical sciences in their current state, and then clarifying their foundations. This conception of the links between philosophy and sciences leads to four comments. First comment, they are the privileged object, mathematical sciences, of any philosophical critique, so to speak, critique philosophique, which aims at isolating the principles underlying these mathematical sciences. Second comment, these principles are not intra-scientific. The object of a philosophical investigation cannot be assimilated to scientific content, which means that philosophy is irreducible to sciences. Third comment, Coutura intends to resolve afresh the question of the applicability of mathematics to experience, which he reduces step by step to the question of the relationship between pure and applied mathematics, with a focus on analysis. And fourth comment, This leads him to identify the ideas that serve as the foundation of mathematics and to understand the rational connection, l'enchaînement rationnel, between such ideas. So Couturat closely associates analysis with developments in infinitesimal calculus, which brings into play two ideas on which the whole analysis rests, namely the ideas of infinity and continuity. At that time, Couturat considers analysis to be the unifying instance of pure and applied mathematics. He points out that analysis, I quote him, gradually penetrates and invades all the natural sciences as they become exact by reducing their objects to measurable magnitudes. Indeed, analysis constructs a priori all conceivable relations between magnitudes and deductively studies their properties and transformations. Of course, when he uses the expression constructs a priori, he refers to Kant. By adopting a long-term scale of observation, Couturat inherited a conception of scholarly mathematics, mathematics which was taught at universities in France, which was dominated by analysis, at least throughout the first half of the 19th century. I can refer here to Caroline Gerhard in particular. And Couturat, in his 1896 work, neglected the theory of substitutions, group of substitutions, which was taught at universities, and which profoundly altered this image of mathematical sciences as dominated by analysis. Couturat was also aware of the mathematical contributions that between the 1860s and the 1890s focused specifically on the foundations of analysis, a question he felt deserved to be addressed from a philosophical perspective. More specifically, Couturat's reflections on analysis enable him to take a fresh look at two problems inherited from Kant. First problem, to clarify the conditions of possibility of synthetic a priori judgments in mathematics. Second problem, to justify the application of mathematics to natural sciences. As Braverman underlined, Couturat's interest in Kant's philosophy of science is due to Charles Renouvier, first, but also to Alphonse Darlu, who was the professor of the three founders of the Revue de Métaphysique et de Morale, but also Couturat's professor at the Lycée Condorcet before Couturat entered the École Normale Supérieure. And we have found some lecture notes relating to Darlu's professorship at the Lycée Condorcet. And there is an important use of Kant for the critique of empiricism, the redefinition of metaphysics, work on the different meanings of idealism, and to emphasize the necessity of the transcendental approach involving knowledge of the laws of the mind and the conditions of possibility of the sciences. Accordingly, in his doctoral thesis, Couturat relies on Kant to criticize empiricism. He understands metaphysics as a system of principles governing the natural sciences. And finally, he also uses a transcendental approach to draw out the laws of the mind. Couturat also echoes a major publishing event, namely the first French translation of Kant's Metaphysische Anfangsgründe der Naturwissenschaft in 1891, and he clearly referred to this translation at the very beginning of his doctoral thesis. Okay, second part, the idea of magnitude as a rational intuition. So here is how Couturat, in his thesis, connects the problem of the foundation of analysis with that of the relationship between the ideas of number and of magnitude. If we believe the mathematicians, analysis will be by Couturat. Analysis